Have you ever gazed up at the night sky, tracing the familiar belt of Orion, and wondered just what mysteries might be shimmering within that hazy patch of light below it? That faint, glowing cloud is no ordinary star. It's the Orion Nebula, a colossal stellar nursery over 1,300 light-years away, where stars are born in breathtaking chaos and beauty. But behind its serene appearance lies a world of astonishing phenomena that defy our understanding of the universe. From colossal protoplanetary disks wider than our solar system to mysterious structures that look like cosmic waterfalls, the Orion Nebula is home to some of the most bizarre and unexplained wonders ever observed. Today, we're embarking on a journey deep into the heart of this cosmic marvel, exploring 30 of its strangest and most captivating secrets phenomena that continue to leave even the most seasoned astronomers utterly baffled. We'll uncover how newborn stars shoot out jets of matter at nearly 500,000 miles per hour, how swirling disks of dust and gas hint at the birth of alien worlds, and how eerie, shadowy formations seem to defy the very laws of physics. This is more than a tour of deep space. It's an invitation to witness the raw, untamed creativity of the universe itself, unfolding in real time. So settle in and open your mind to the extraordinary. Whether you're a seasoned stargazer or someone who's simply curious about the cosmos, what you're about to discover will challenge everything you thought you knew about star formation, cosmic structure, and the very nature of reality. This is a story written in light and shadow, gravity and gas, a story that reminds us just how much wonder still awaits, hidden in plain sight within the depths of space. Our journey into the Orion Nebula's deepest secrets begins not with a brilliant star or a swirling disk of light, but with a shadow. Cutting across the nebula's glowing heart are strange, dark features known to astronomers as the Orion Bars. These are not solid structures but immense, dense lanes of cosmic dust and gas, standing out in stark silhouette against the brilliant background glow. What makes them so peculiar is their appearance. They aren't wispy or chaotic like many other dusty regions in space. Instead, they are remarkably sharp and linear, almost like great dark walls that have been drawn with a ruler. This geometric precision is the first clue that something very unusual is happening here, something that defies the normally turbulent and unpredictable nature of nebula physics. These bars act as a cosmic laboratory, demonstrating a fundamental process on a truly colossal scale. They are the front line of a dramatic interaction between the intense ultraviolet radiation blasting from the nebula's hottest, youngest stars, most notably the massive stars of the Trapezium Cluster, and the cold, primordial gas and dust that surrounds them. That powerful starlight is literally carving into the nebula, and the Orion Bars represent the shock front where this incredible energy meets resistance. Imagine a glacier slowly advancing, its leading edge a steep, crumbling cliff face. The bars are that cliff, but made of gas and dust, constantly being eroded by the stellar winds. This process, called photodissociation, is where the harsh radiation breaks apart molecules, but it's at this very boundary that new stars are given the ingredients they need to form. Scientists believe these dark bars are far more than just passive obstacles. They are likely crucial cradles for the next generation of stars. As the radiation pressure compresses the material in these dense lanes, it can trigger gravitational collapse within the clouds. Pockets of gas and dust become squeezed to the point where they can no longer support their own weight, causing them to coalesce and ignite new stars. It's a beautiful and violent cycle. The very energy from massive stars that destroys also creates, forging new solar systems in the dark shadows it casts. The Orion Bars, therefore, are a stunning visual representation of the life cycle of a nebula, a dynamic interface where destruction and creation are two sides of the same cosmic coin. But if you think the dark geometry of the Orion Bars is a spectacle, wait until we peer even deeper into the nebula's heart, where an object so strange and brilliant hides that it fundamentally reshapes our view of stellar adolescence. This is the Becklin-Neugebauer Object, a name that sounds like it belongs in a spy thriller, and in many ways its story is just as covert. Discovered in the 1960s by astronomers Erich Becklin and Jerry Neugebauer, this wasn't found by peering through a traditional visible light telescope. Instead, it revealed itself only through the infrared eye, a telltale sign that we're dealing with something shrouded, something that doesn't want to be seen directly. The reason for its secrecy is its location. The BN object is buried within the dense, murky core of the Orion molecular cloud, a region so packed with gas and dust that it's completely opaque to visible light. It's like trying to spot a lighthouse through a thick, impenetrable fog. You can't see the beam itself, but you can detect the immense heat and energy it's generating. And generate energy it does. The Becklin-Neugebauer object is an incredibly powerful infrared source, blazing with the warmth of a young star still swaddled in its natal blanket. This isn't just any infant star, though. The sheer intensity of its glow suggests a truly massive protostar, one that might be as much as 15 times the mass of our own Sun, caught in the very act of gathering material from its surrounding cocoon. What makes this object so enigmatic, however, is its motion. Precise observations over decades have revealed something startling. The Becklin-Neugebauer object is not sitting still. It's hurtling through its dense environment at a tremendous speed, around 30 kilometers per second. This fierce movement creates a bow shock in front of it, much like the wave that builds up at the front of a speedboat, plowing through the surrounding gas and dust. This violent passage suggests a dramatic past. The prevailing theory is that this colossal newborn star wasn't born in isolation. It was likely part of a multiple star system, a cosmic sibling rivalry that ended in a gravitational confrontation. This chaotic encounter could have catapulted the BN object out of its birthplace, sending it on a high-speed journey through the nebula, lighting up the darkness around it as it goes. So, while it appears as a single point of hidden light, its story is one of chaos, ejection, and a fiery youth spent on the run. Yet for all its fiery spectacle, the Becklin-Neugebauer object is far from the only hidden drama unfolding within the nebula's depths. Some of the most breathtaking structures are not revealed by the light they emit, but by the shadows they cast against the glowing cosmic canvas. These are the legendary pillars of creation, though within Orion, they manifest as a different kind of formation altogether. Eerie, elongated structures often called the fingers of Orion. If the Orion Bars are great dark walls, these pillars are the towering, weathered spires that rise from them, sculpted by the same intense stellar winds into shapes of haunting and almost biological beauty. These so-called fingers are not solid objects you could touch. They are colossal clouds, light years in length, composed of incredibly cold molecular hydrogen gas and fine, sooty dust. They stand in stark, dramatic silhouette against the brilliantly illuminated background of the nebula, their tips glowing with a soft, ethereal light where the radiation from nearby massive stars is slowly eroding them away. This process, known as photoevaporation, is what gives them their distinctive finger-like appearance. The densest knots of gas and dust at the top of each pillar are more resistant to the eroding stellar winds, acting like protective shields that leave long, trailing columns of material in their shadow. It's a cosmic balancing act on a monumental scale, where the destructive force of starlight paradoxically sculpts the very nurseries where new stars are born. Within the dark, sheltered hearts of these pillars, the conditions are perfect for star formation. Shielded from the harsh external radiation, the dense gas can cool and collapse under its own gravity. Telescopes like Hubble and Webb have peered directly into these cosmic wombs, revealing glowing protoplanetary disk proplyds and the faint, nascent sparks of infant stars. Each finger is in essence a bustling stellar nursery, its serene exterior hiding the violent and magnificent chaos of birth happening within. The iconic Hubble images of similar structures in other nebulae have seared this beautiful paradox into our collective consciousness, a scene of apparent tranquility that is actually a snapshot of continuous and catastrophic change. The haunting beauty of these structures is matched only by their fleeting nature. In the grand timeline of the cosmos, they are temporary wonders. The same stellar winds that sculpt them will eventually shred them completely, exposing the newborn stars within to the wider nebula and dissipating the pillar into the surrounding cloud. We are witnessing them in a single, glorious moment of their existence, a testament to the constant cycle of creation and destruction that defines these cosmic landscapes. It is a poignant reminder that the universe is both an artist and a destroyer, carving breathtaking monuments not in stone but in gas and time itself. Yet, even as these majestic pillars are slowly worn away by the stellar winds, the very source of that destructive power holds mysteries of its own. At the very core of the Orion Nebula, blazing with an intensity that shapes everything around it, lies the Trapezium Cluster. This tight-knit group of hot, young stars is the brilliant engine room of the entire nebula, but a closer look reveals that this stellar nursery is anything but orderly. The brightest members, easily spotted through a small telescope, are just the beginning of the story. In reality, the Trapezium is a teeming metropolis of over 1,000 stars, all crammed into a space just a few light years across, and the dynamics within this crowded city are producing some of the most head-scratching anomalies astronomers have ever witnessed. One of the most immediate puzzles is the motion of these stars. In a stable cluster, you'd expect the stars to orbit a common center of gravity in a somewhat predictable fashion. But here, precise measurements from telescopes like the Hubble have shown that many stars are not following the script. They are zipping around at astonishing and seemingly random velocities, with some moving at speeds that defy easy gravitational explanation. This isn't the serene ballet of a mature star cluster. It's more like a chaotic mosh pit of stellar bodies. The leading theory suggests that these erratic paths are the result of violent gravitational interactions. In such a densely packed environment, close encounters between stars are common, and these cosmic near collisions can slingshot stars away at incredible speeds, effectively ejecting them from the cluster altogether over time. This constant gravitational turmoil might explain why the trapezium seems less densely packed than models predict it should be. It's literally throwing its own stars out into the cold depths of space. Beyond this stellar chaos, the cluster is also a source of baffling energy emissions. The intense ultraviolet radiation that illuminates the nebula is expected, but astronomers have also detected powerful and fluctuating X-ray flares coming from these young stars that are hundreds, even thousands of times more energetic than anything our Sun emits. These aren't the gentle flickers of a settled middle-aged star. These are colossal, violent tantrums. The cause is believed to be linked to the incredibly strong magnetic fields of these stellar infants. As a young star rotates, its magnetic field lines can become twisted and tangled, storing enormous amounts of energy until they suddenly snap and reconnect, releasing a cataclysmic burst of X-rays in a process similar to a solar flare, but on a truly monstrous scale. This constant, high-energy barrage profoundly impacts the surrounding environment, heating the gas in the nebula and potentially influencing the chemistry of the planet, forming disks around other, quieter stars in the cluster. Perhaps the most profound anomaly, however, is the apparent age of the stars themselves. Stellar astrophysics provides us with a well-tested playbook for how stars of a given mass should evolve. By measuring a star's brightness and temperature, we can place it on a chart called the Hertzsprung-Russell diagram and accurately estimate its age. But in the Trapezium Cluster, this playbook seems to have been thrown out the window. Stars of identical mass are appearing at vastly different points on this diagram, suggesting a wide spread of ages that simply shouldn't exist in a cluster thought to have formed from a single cloud of gas in one relatively brief event. Some stars look millions of years older than their neighbors. This age-spread anomaly challenges the very fundamentals of how we think star clusters are born. It's possible that star formation here wasn't a single, brief burst but a drawn-out process lasting millions of years. Alternatively, the answer might lie with the star's frenetic environment. The intense radiation from massive stars could be stripping away the outer layers of smaller, cooler stars, making them appear hotter, brighter, and therefore older than they truly are. Or the gravitational slingshot encounters that send stars flying could also disrupt their internal structure, altering their development in ways we don't yet fully understand. The Trapezium Cluster, for all its brilliant light, forces us to admit that the early lives of stars are far more complex and turbulent than our textbooks once claimed. But the true enigma of OMC1 lies deeper within its structure, in pockets of intense heat and bizarre chemistry that defy all expectations. Scattered throughout this cold, dark cloud are what astronomers call hot cores. These are small, incredibly dense regions blazing with surprisingly high temperatures, sometimes reaching over 100 Kelvin, which is far hotter than the frigid material surrounding them. In a place where the average temperature is just a dozen or so degrees above absolute zero, these localized hotspots are as unexpected as finding a roaring bonfire at the center of an iceberg. Their existence in such a young stellar nursery is a major puzzle. Conventional wisdom suggests that hot cores should only appear later, after a massive protostar has ignited and begun to heat its immediate surroundings. But here they are, present before that pivotal moment, forcing a complete rethinking of the earliest stages of star birth. The heat within these cores is only half the mystery. The other half is the astonishingly complex chemical soup found within them. Using powerful radio telescopes, scientists have detected the spectral fingerprints of molecules in OMC1 that are far more sophisticated than simple hydrogen or carbon monoxide. We're talking about complex organic molecules, the kind that are considered the very building blocks of life. These include things like methanol, formaldehyde, and even dimethyl ether. Finding such advanced chemistry in what is supposed to be a cold, pristine, and primordial environment is like walking into an empty warehouse and finding a fully cooked 5-course gourmet meal sitting on the floor. It shouldn't be there. The cold temperatures should prevent these complex molecules from forming, as atoms and simpler molecules lack the energy to create the necessary chemical bonds. Their presence suggests that the chemistry within these dense cores is far more active and efficient than any of our models predicted. So how do you get a hot core with complex chemistry in a cold cloud? The leading theory points to a dramatic and violent beginning. The incredible turbulence and shockwaves rippling through OMC1, likely caused by the explosions of ancient, long-dead stars or the powerful outflows from newborn ones nearby, could be providing the necessary energy. These shockwaves compress the gas, heating it up rapidly for a brief period, and this surge of energy might provide the kick needed for simple molecules to combine into more complex ones. It's a form of cosmic flash cooking where a sudden, intense event jump starts a rich chemical process before the region has a chance to cool back down. This means the ingredients for life, the complex organic molecules, might be forged not in the calm around mature stars, but in the violent, chaotic birth cries of the stars themselves, embedded deep within these mysterious molecular clouds. But the turbulent history of the Orion Nebula is not written only in the chaotic motions of its stars or the complex chemistry of its clouds. It is also etched across the cosmos in the form of vast, expanding shock waves, the lingering echo of a cataclysm so powerful it must have been seen across the galaxy. This brings us to one of the region's most dramatic cold cases, the BNKL explosion remnant. The name itself is a jumble of letters, a technical label for a detective story written in gas and motion. While the Trapezium Cluster is the nebula's present-day engine, evidence suggests that a far more violent event occurred here in the astronomically recent past, an explosion of such staggering force that its remnants are still sculpting the environment today. So, what is the evidence for this ancient detonation? Astronomers mapping the nebula in radio waves discovered something extraordinary. Multiple massive streams of molecular gas, all flowing outward from a single central point near the Becklin-Neugebauer Object and the Kleinman-Low Nebula, hence the BNKL designation. This isn't a gentle, steady flow like a river. This material is being blasted outward at tremendous speeds, up to hundreds of kilometers per second, forming immense lobes and filaments of matter that stretch for light years. The sheer kinetic energy required to propel this much mass so quickly is almost incomprehensible. It is equivalent to the energy our Sun will release over its entire 10 billion-year lifetime, but ejected in a single, catastrophic instant. The shock fronts from this event are still plowing through the surrounding molecular cloud, compressing gas, triggering new star formation, and carving out caverns within the nebula, like the wake of a bomb that went off centuries ago but whose wave is still rolling across the ocean. The central mystery, the whodunit of this cosmic crime scene, is what could have possibly caused such an immense explosion. Several compelling theories are on the table, each more fantastic than the last. The first and perhaps most straightforward suspect is a runaway stellar merger. In the densely packed core of the young cluster that existed here, two massive protostars could have spiraled into each other and collided. The energy released from such a titanic impact would be apocalyptic, easily accounting for the observed energy and the symmetrical ejection of material. It would be a true cosmic fireball, a brief, brilliant flash signaling the violent death of two infant stars and the birth of something new. A second, even more exotic theory proposes the explosive disintegration of an entire young star cluster. If a group of stars formed too close together in an unstable configuration, their gravitational interactions could have become so chaotic that the entire system flew apart in a rapid, energetic event called cluster ejection. This wouldn't be a single flash of light, but a gravitational unraveling that transferred immense energy to the surrounding gas, effectively blowing a bubble in the cloud. Yet a third possibility ventures into the realm of truly exotic physics, the idea of a massive star that collapsed directly into a black hole without the traditional supernova explosion. In this hypothetical failed supernova scenario, the star's core would collapse silently into a black hole, but a vast reservoir of energy stored in its rapidly rotating outer layers could be suddenly released, rocketing away from the new black hole in a colossal outburst. Each of these theories has its merits and its drawbacks, and astronomers continue to analyze the precise motions and chemistry of the outflowing gas for clues, trying to determine which apocalyptic scenario best fits the forensic evidence left behind. What is undeniable is the ongoing impact of this ancient event. The shock waves from the BNKL explosion are not merely a fossil record, they are active and powerful shapers of the Orion Nebula's current landscape. These expanding walls of pressurized gas act like cosmic bulldozers, sweeping up material and crushing it into new, dense layers. In many places, this compression is likely the trigger that pushed cold, quiet pockets of gas over the edge into gravitational collapse, igniting a new generation of stars that owe their very existence to that long-ago catastrophe. The explosion was an event of pure destruction, yet it simultaneously became a catalyst for creation, demonstrating the perpetual cycle of death and rebirth that defines this dynamic stellar nursery. Its lingering shock waves are a permanent reminder that the serene beauty of a nebula often masks a violent and energetic history. Beyond the brilliant core and the dark, sculpted pillars lies an even grander structure, one so immense and faint that it often escapes the notice of casual observers. This is the Orion Veil, a vast and enigmatic curtain of glowing gas that envelops the entire nebula complex. Unlike the dense, knotty clouds at the heart of Orion, The veil is incredibly tenuous, a wispy expanse of ionized plasma that stretches for dozens of light years. Its ethereal glow comes from the same process that lights the main nebula. The fierce ultraviolet radiation from the trapezium stars is stripping electrons from hydrogen atoms, causing them to emit that characteristic red light when they recombine. But the veil is far enough from the core that this light is faint, a delicate shroud draped around the brilliant chaos within. For a long time, it was considered a relatively simple structure, a mere outer fringe of the main event. However, closer inspection has revealed that this veil holds secrets that are fundamentally challenging our understanding of how such nebulae live and die. The first major puzzle is its sheer shape and location. The Orion Veil isn't a uniform shell. It's a collection of intricate filaments and loops, a chaotic tapestry that suggests a far more violent origin than simple, steady expansion. Detailed observations, particularly from space telescopes, show that this structure is actually the inner wall of a gigantic bubble. The prevailing theory is that this bubble was blown clear by the combined effect of two powerful forces: the stellar winds from massive stars and the cataclysmic shock waves from supernova explosions that occurred long before the trapezium stars we see today were even born. This means the veil is a fossil record, the lingering boundary of ancient, apocalyptic events that reshaped this entire region of space millions of years ago. We are not just looking at a static cloud, we are looking at the scar tissue from the nebula's own turbulent birth. This ancient origin story leads directly to the veil's second, and perhaps most baffling mystery, its motion. By carefully measuring the Doppler shift in its light, astronomers can map how this massive structure is moving. The results are deeply confusing. Different sections of the veil are moving in wildly different directions and at different speeds. Some parts are racing towards us while others are speeding away, and still others seem to be moving almost tangentially. This isn't the orderly, predictable expansion one would expect from a single, ancient explosion. Instead, it looks more like the aftermath of multiple, overlapping cataclysms, a series of bubbles blown at different times that are now colliding and interacting with each other in complex ways. The dynamics are so chaotic that they contradict simpler models of nebula evolution, forcing scientists to account for a history filled with repeated bursts of stellar feedback and violent energy release. The final layer of this enigma involves its unusual ionization patterns. The veil should, in theory, have a relatively straightforward gradient of ionization. The side facing the Trapezium Cluster should be highly ionized, blasted by the direct light of the massive stars, while the far side should be progressively more neutral. Yet observations reveal a much patchier and less predictable pattern. There are highly ionized regions surprisingly far from the core, and conversely, pockets of neutral gas that seem to persist much closer to the radiation source than should be possible. This suggests that the veil is not a smooth wall but a profoundly lumpy and porous one, full of dense knots and empty tunnels that allow radiation to seep through in unexpected ways. These dense knots can shield pockets of gas behind them, creating shadowed regions where atoms remain neutral, while fissures in the structure allow energetic photons to travel deep into the veil, ionizing gas far from its inner surface. It's a complex, three-dimensional structure that behaves less like a curtain and more like a labyrinth, where light and matter interact in a constantly shifting and unpredictable dance. The Orion Veil, therefore, is far more than a simple backdrop. It is a dynamic and chaotic interface, a testament to the layered history of violence that has shaped the Orion Nebula. Its contradictory motions and strange ionization are the direct result of millions of years of stellar winds and supernova shock waves crashing into each other, a palimpsest of cosmic energy written across the sky. Understanding its full story is key to unraveling the complete life cycle of not just Orion, but of stellar nurseries across the universe, revealing how the death of one generation of stars literally clears the stage and sets the conditions for the birth of the next. Nestled within the turbulent heart of the Orion Nebula, where fierce stellar winds and searing radiation would seemingly tear apart any delicate structure, lies one of its most beautiful and baffling discoveries, the proplyds. Short for ionized protoplanetary disks, these are the fledgling solar systems in the making, vast spinning platters of gas and dust encircling infant stars. The Hubble Space Telescope's iconic images revealed them not as the featureless blobs astronomers might have expected, but as breathtaking, sculpted forms. Some appear as elegant teardrops, their heads pointed directly at the destructive power of the Trapezium Cluster's massive stars. Others look like giant, glowing space angels or delicate umbrellas with long, shadowy tails streaming away behind them. Their very existence here is a paradox. How can these fragile cradles of future planets possibly survive in what is essentially a cosmic demolition derby? The answer lies in a delicate and constant battle between creation and destruction. The same intense ultraviolet radiation that threatens to evaporate these disks is also responsible for their gorgeous, illuminated shapes. For a proplyd that is facing a massive star head-on, the radiation blows away the outer layers of its gas, creating a shock front that glows brilliantly and forms that distinctive teardrop or umbrella-shaped head. The material that gets stripped away is then carried downstream by the stellar wind, forming the long, dark tail we see trailing behind it. It's a tragic, beautiful erosion happening in real time. Astronomers can even calculate the mass loss and estimate the lifespan of these disks under such an onslaught. For many, the numbers are grim. Some of the smaller disks are losing mass so rapidly they may completely evaporate within the next 100,000 years. A blink of an eye in cosmic terms, potentially robbing them of the chance to ever form planets. This leads to a startling implication. The very environment that creates stars might also prevent them from building planetary systems. It creates a cosmic lottery where a proplyd's survival depends heavily on its location and its own mass. A disk that forms farther from the trapezium's brilliant bullies has a much higher chance of surviving long enough for dust grains to clump together into planetesimals and eventually planets. A more massive disk, even if it's closer to the radiation source, might have enough material to weather the storm of photoevaporation and still have plenty of gas and dust left over for planet formation. Our own solar system likely formed in a much quieter, more isolated stellar nursery, spared from such a violent childhood. The proplyds of Orion show us that the path to becoming a star with planets is not guaranteed. It is a race against time and a fight against the elements, a struggle that many of these infant systems will ultimately lose. Yet within this hostile environment, the varied shapes and sizes of the proplyds tell a more nuanced story than simple destruction. Their diverse forms are a direct window into their individual experiences. A symmetric, comet-shaped proplyd is likely situated directly in the line of fire from a massive star, while a more rounded or irregular one might be partially shielded or oriented at a different angle. Some even appear as dark, compact silhouettes against the bright nebula. These are the lucky ones, seen from an angle where their dense inner disk completely blocks the background light, suggesting they are massive and potentially robust. This variety is a goldmine for astronomers, providing a living catalogue of how protoplanetary disks interact with their environment. By studying them, we can understand the processes that either doom a disk to dissipation or allow it to persevere long enough to create the seeds of new worlds. Perhaps the most profound revelation from these objects is what they tell us about the raw materials for planet formation. Spectroscopic studies of proplyds have detected the fingerprints of numerous molecules and minerals within them, including silicates and complex carbon compounds, the very building blocks of rocky planets and potentially life. The fact that these materials are present and persisting, even under extreme duress, suggests that the basic ingredients for planets are incredibly resilient. The chaos of Orion isn't just a story of loss, it's also a story of purification and resilience. The external radiation might be boiling away the lighter gases, potentially leaving behind a richer concentration of heavier dust and rocks in the inner disk, which could actually accelerate the formation of rocky, terrestrial planets like our own. In the midst of apparent chaos, the universe might be employing a brutal but effective refining process. While the proplids show us the struggle of infant solar systems to hold onto their planet-forming material, some of the youngest stars in the Orion Nebula are not just passively enduring their violent environment, they are actively fighting back with spectacular, high-energy outbursts of their own. These are the Herbig-Haro objects, and they represent some of the most visually striking and physically violent phenomena in any stellar nursery. At first glance, they look like delicate, glowing wisps or tiny, faint smudges of nebulosity. But don't let their ethereal appearance fool you. Each one is a cosmic bullet train, a supersonic jet of matter screaming across space at speeds that can exceed 500,000 miles per hour. These are not static clouds, they are the fiery aftermath of a tremendous ejection, the shock waves from material that was violently launched from the poles of a deeply embedded protostar just a few thousand years ago. The process that creates these brilliant displays begins in the chaotic heart of a collapsing gas cloud. As a protostar forms, it doesn't just quietly gather material. It draws in gas and dust from a spinning disk that surrounds it, but not all of that matter makes it onto the star's surface. Instead, some of it gets channeled along the protostar's incredibly powerful magnetic field lines and is then catapulted outward from its poles in two opposing, narrow beams. This is a fundamental release mechanism for the star's angular momentum, a way for it to shed excess energy as it contracts. When these incredibly fast-moving jets slam into the slower-moving gas of the surrounding interstellar cloud, the result is a spectacular shock wave. The collision is so violent that it heats the gas to temperatures high enough to make it glow, creating the luminous knots and bow shocks that we identify as a Herbig-Haro object. It's akin to turning on a garden hose in a dusty room and seeing the precise shape of the jet revealed by the dust it pushes ahead of it, only on a scale that is almost unimaginably vast and energetic. What makes these objects so mysterious, however, is their bizarre and varied structure. They are rarely simple, straight lines. Instead, they often appear as a series of glowing, curved beads or multiple bow shocks, one nestled inside the other, looking like a ghostly cosmic partner to a smoke ring. This complex morphology tells a story of a star that is not ejecting material in a steady stream, but in fits and starts in powerful, episodic outbursts. Each new pulse of ejected material travels faster than the one before it, eventually catching up and plowing into the slower-moving previous ejection, creating that distinctive chain of shock knots. The shapes are a direct record of the protostar's violent and erratic infancy, a timeline of its tantrums written across light years of space. Some Herbig-Haro objects even show clear precession, meaning the jet is wobbling like a slowing top, causing it to sweep out a S-shaped or corkscrew path through the nebula. This wobble could be caused by gravitational interactions with a binary companion star, or by the complex, unstable dynamics of the inner accretion disk itself. The biggest unanswered question surrounding these phenomenal structures is the precise engine that drives them. We know the general mechanism involves magnetic fields and accretion, but the details of how a young star can accelerate such immense quantities of matter to such phenomenal speeds remain a major topic of research. The energies involved are staggering, often exceeding the total output of the protostar itself. It's an efficiency that defies simple explanation. Furthermore, the composition of the jets adds another layer of intrigue. Spectroscopy reveals they are not just made of simple hydrogen gas. They contain molecules like silicon monoxide and even iron, meaning they are scouring up and launching material from the very inner, hottest regions of the protoplanetary disk, close to the newborn star. This process does more than just create a light show. It fundamentally shapes the future of the star system. By ejecting mass and energy so forcefully, the jet clears a cavity around the protostar, potentially affecting how much material it can ultimately accumulate and even influencing the formation of planets in the outer regions of the disk. In their breathtaking beauty, Herbig-Haro objects are a powerful reminder that the birth of a star is not a gentle process, but a violent, spectacular, and beautifully chaotic event. Yet the mysteries of the Orion sword are not confined to any single wavelength of light. As we venture beyond the visible spectrum and into the realm of radio waves, a whole new layer of peculiar phenomena reveals itself. The region is a cacophony of natural radio emissions, a symphony of hisses, pops, and whistles generated by the frenetic dance of atoms and molecules in the turbulent gas. But nestled within this expected cosmic static are signals that defy easy categorization, strange, intermittent radio anomalies that have sparked both rigorous scientific inquiry and more than a little speculation. These aren't the structured, repeating signals one might hope for from an intelligent civilization. They are more like ghostly echoes, brief and powerful bursts of energy that appear and vanish without warning, leaving astronomers scrambling for an explanation. One of the most persistent puzzles involves specific, unexplained frequencies that seem to originate from deep within the molecular cloud. Radio telescopes tuned to listen for the faint whispers of molecules like water or methanol sometimes pick up intense, narrow-band emissions at frequencies that don't correspond to any known chemical transition. It's like tuning a radio dial and suddenly finding a powerful station broadcasting on a frequency that, according to all your engineering manuals, shouldn't exist. These mystery lines suggest the presence of molecules or physical processes we have yet to discover or fully understand. The leading theory points to highly excited states of common molecules. In the extreme environment near a massive protostar, molecules can be pumped so full of energy that they emit at frequencies that are simply not seen in quieter, calmer regions of space. It's a form of cosmic chemistry under pressure, creating a unique spectral fingerprint that we are only just beginning to decode. Beyond these strange frequencies are the truly enigmatic intermittent signals. These are not steady emissions but sudden, short-lived bursts of radio noise that can last from a few hours to a few days before fading back into the background. Their unpredictability makes them incredibly difficult to study. By the time a telescope is swung into position to get a detailed look, the event is often over. The most plausible explanations for these flickers lie in the violent tantrums of the nebula's youngest stars. Flares from young stellar objects, hundreds of times more powerful than anything our Sun produces, could easily generate brief, intense pulses of radio waves as accelerated particles slam into the surrounding gas. Similarly, the accretion process itself, where clumps of materials suddenly crash onto the surface of a protostar, could release a sharp burst of energy across multiple wavelengths, including the radio. However, the sheer power and strange characteristics of some of these signals have led to more speculative, albeit fascinating, possibilities. Some astronomers have entertained the idea that we might be detecting the aftermath of cataclysmic events, like the collision of extremely dense, planet-sized bodies within the protoplanetary disks of young stars. Others have pondered whether powerful magnetic phenomena, like star-disk interactions or even the ignition of a protostar's magnetic engine, could generate such brief, intense radio flashes. And while it remains firmly in the realm of remote possibility, the spectral strangeness has even prompted a few to cautiously wonder if we could be seeing the faint, unintentional signature of something else entirely, not a natural process but a technological one. This is, of course, the most extreme hypothesis and is considered highly unlikely by the vast majority of scientists who continue to search for a natural astrophysical origin. Yet the very existence of these unexplained signals serves as a thrilling reminder that even in our own cosmic backyard, there are still phenomena that challenge our catalogue of known physics, urging us to look closer and think bigger about the chaotic and wondrous processes at play in this stellar nursery. But if we shift our gaze away from these brilliant, energetic displays and into the shadows, we find a phenomenon defined not by what it emits but by what it absorbs. Deep within the sprawling expanse of the Orion Nebula complex lies a region of profound and unsettling darkness known as the Dark Bay. This is not one of the sculpted, photogenic pillars we discussed earlier. This is something far more vast and enigmatic. It appears as a massive, amorphous void, a great gulf of nothingness that seems to swallow light itself. While the surrounding nebula glows with the vibrant energy of newborn stars, the Dark Bay is a silent, opaque abyss, a cosmic blind spot that raises a deeply intriguing question. In a region bursting with the raw material for star birth, why does this particular pocket of space appear so utterly and completely dead? The key to its darkness is its incredible density. The Dark Bay is not empty, on the contrary, it is likely one of the densest concentrations of cold molecular gas and dust in the entire Orion complex. This material is so thick and tightly packed that it becomes completely impenetrable to visible light. The photons from the Trapezium Cluster and other brilliant stars simply cannot pass through it. They are either absorbed by the countless dust grains or scattered away, making this region appear as a featureless black patch against the glowing background. It's the difference between a clear summer sky and a thick, impassable fog bank. One allows light to travel freely, while the other traps and diffuses it. In many ways, the Dark Bay represents the nebula in its most primordial, unprocessed state, a preserved relic of the cold, dark cloud that first collapsed to form all the brilliant stars we see around it. This leads to the central paradox of the Dark Bay, the true source of its mystery. According to all our established models of star formation, this region should be a hotbed of stellar activity. It possesses the two key ingredients needed for star birth in abundance: an immense amount of mass and the crushing pressure of its own gravity. We would expect to see the telltale signs of collapse within it, the warming kernels of protostars beginning to ignite, the powerful jets of Herbig-Haro objects punching through the gloom, or at least the subtle infrared glow of dense cores warming up. Yet, detailed surveys from infrared and radio telescopes reveal a startling lack of these activity markers. The region is suspiciously quiet. It's as if you walked into a warehouse filled to the ceiling with all the parts needed to build a car, along with the tools and instructions, yet found no evidence that any assembly had ever begun. This absence of star formation defies our expectations and suggests that some other, unseen force is at work here, actively suppressing the natural process of gravitational collapse. So what could be holding back the tide of star birth within this cosmic reservoir? Astronomers are investigating several compelling possibilities. The first is that the cloud may simply be too young. Star formation might not have yet begun in earnest within its core, and we are seeing it in a brief, precarious state of equilibrium before the inevitable collapse commences. Another theory points to the influence of powerful magnetic fields. These invisible lines of force woven through the cloud can provide a form of structural support, exerting pressure that counteracts gravity and prevents the gas from fragmenting and collapsing. It would be like a vast, invisible scaffold holding up the entire structure, delaying its inevitable downfall. Perhaps the most fascinating hypothesis involves turbulence. The Dark Bay may not be the serene, quiet pool it appears to be from the outside. Internal motions, powerful supersonic waves rippling through the gas, could be churning the material, keeping it stirred up and preventing it from settling into the stable, dense knots required to form stars. This would be like trying to form a snowball in the middle of a hurricane. The constant buffeting would prevent any flakes from sticking together. This turbulence could be a leftover from the cloud's own violent formation, or it could be driven by external influences such as the shock waves from those ancient supernovae that shaped the Orion Veil, still echoing through this region and keeping the gas perpetually agitated. The enduring mystery of the Dark Bay forces us to confront the fact that star formation is not a simple, guaranteed process. It is a delicate balance between competing forces, gravity versus pressure, collapse versus support. This dark region is a monument to that balance, a place where the scales have, for now, been tipped against creation. Its silence is not an absence of story, but a chapter that has yet to be written. It holds within its light-absorbing depths a vast reservoir of potential, a future generation of stars and planets waiting for the trigger that will one day ignite a new wave of cosmic birth, forever changing the face of the Orion Nebula. At the very heart of this cosmic storm, blazing with an intensity that dominates the entire Orion Nebula, lies the star Theta-1 Orionis C. It is the primary engine of the entire system, a colossal O-type star that is the brightest and most influential member of the Trapezium Cluster. This is the star whose fierce ultraviolet radiation ionizes the surrounding gas, causing the nebula to glow. It is the source of the stellar winds that sculpt the propylids and erode the pillars. In many ways, Theta-1 Orionis C is the undisputed monarch of this celestial realm. Yet, for all its apparent power and stability, closer observation reveals that this monarch is deeply troubled, exhibiting a set of behaviors so strange and contradictory that they have become one of the most enduring enigmas in modern astrophysics. The first and most baffling anomaly is its unpredictable variability. This is not a steady, constant beacon. Theta-1 Orionis C undergoes strange and irregular fluctuations in its brightness. These aren't the rhythmic pulsations seen in some variable stars. They are erratic, sometimes dramatic changes that occur over surprisingly short timescales, from weeks down to just a few days. For a star of its immense size and mass, roughly 40 times that of our Sun, and burning at a surface temperature of over 40,000 degrees Celsius, this level of instability is utterly unexpected. A star this massive should have a vast, stable interior, its output governed by the steady and immense fusion processes at its core. This flickering suggests that something is interfering with the transport of energy from the core to the surface, creating a kind of stellar stutter. One leading theory points to the possibility of a powerful magnetic field, orders of magnitude stronger than anything we've directly measured in such a hot star, twisting and tangling within its plasma and temporarily bottling up energy before releasing it in bursts. This leads directly to the second great mystery, its wind. Massive stars like this one are known for their powerful stellar winds, streams of charged particles blown from their surfaces at incredible speeds. The wind from Theta-1 Orionis C is indeed powerful, but it is also profoundly peculiar. Instead of flowing away from the star in a relatively uniform spherical shell, as standard models predict, observations suggest its wind is highly structured and shockingly weak for a star of its class. The measured mass loss rate, the amount of material it is actually ejecting into space, is significantly lower than theorists would expect. It's as if a hurricane-force wind were somehow confined to a few gusty corridors rather than spreading out in all directions. The prevailing explanation for this strange behavior again revolves around the hypothetical magnetic field. Astronomers suspect Theta-1 Orionis C possesses a complex, tilted magnetic field that channels its wind, funneling the outflow along the magnetic field lines and concentrating it primarily at the star's magnetic equator. This would create a disc-shaped wind, or two opposing jets rather than a sphere, dramatically altering its interaction with the surrounding nebula and explaining the unexpectedly low total mass loss. Perhaps the most compelling evidence for this magnetic enigma comes from the star's observed rotation. Theta-1 Orionis C is spinning remarkably slowly for such a young, massive star. It takes about 15 days to complete a single rotation, a leisurely pace compared to the rapid spins of many of its stellar siblings. This slow spin is a major clue. A strong, pervasive magnetic field can act as a brake on a star's rotation, effectively transferring angular momentum from the star to its outflowing wind, slowing it down over time. The combination of its strange variability, its anomalously weak and structured wind, and its sluggish rotation all point toward one extraordinary conclusion. Theta 1 Orionis C may be a rare and fascinating cosmic hybrid, a massively hot star behaving with the magnetic personality of a much cooler, more active star like our Sun. This challenges the very classification system we use for stars, suggesting that magnetism may play a far more important and complex role in the lives of the most massive stars than we ever before realized. But to truly grasp the significance of these hot cores, we must venture beyond the heat itself and into the even more astonishing chemical factory operating within them. In the frigid vacuum of a typical molecular cloud, chemistry is a slow and tedious process. Atoms and simple molecules drift listlessly, rarely mustering the energy to form more complex bonds. It's a barren wasteland, chemically speaking. The Orion hot cores shatter this expectation completely. When astronomers point radio telescopes toward these localized hotspots, they don't just find simple hydrogen or carbon monoxide. They detect the spectral signatures of a veritable organic soup, a rich concoction of complex molecules that include things like methanol, formaldehyde, ethyl cyanide, and even dimethyl ether. Finding such advanced molecular building blocks in what is supposed to be a cold, primordial environment is like discovering a fully stocked, state-of-the-art kitchen in the middle of an untouched Arctic wilderness. It simply shouldn't be there. The presence of these molecules suggests a form of chemistry that is both incredibly efficient and startlingly rapid, forcing a complete rewrite of our models for how the ingredients for life are forged in space. The prevailing theory to explain this chemical enigma is as dramatic as the phenomena itself. Scientists believe the key is a sudden, violent injection of energy, a cosmic flash heating event. The incredible turbulence within the Orion cloud complex, likely driven by shockwaves from nearby stellar winds or even the echoes of that ancient BNKL explosion, could send powerful waves of pressure crashing through these dense cores. Imagine a pressure cooker being rapidly heated. The shockwave compresses the gas, dramatically raising its temperature for a relatively brief but critically important period. This surge of heat provides the energy needed for simple molecules to overcome their barriers and link together into more complex chains. Then, as the region begins to cool back down, these newly formed complex molecules become trapped or frozen out onto the surfaces of cold dust grains, preserving them within the core. This process effectively bakes the complex chemistry into the core before it can dissipate, creating a localized reservoir of organic material. It's a form of interstellar shock therapy, where a sudden traumatic event jump starts a rich and sophisticated chemical process. This has profound implications that reach far beyond Orion itself. The complex organic molecules found in these hot cores are the very precursors to the amino acids and sugars that form the basis of life on Earth. The fact that they can form so quickly and efficiently in the violent, chaotic environment of a stellar nursery suggests that the fundamental ingredients for biology are not rare cosmic luxuries, but could be a common and inevitable byproduct of star formation everywhere. When a star like our Sun was born in a similar cluster billions of years ago, its surrounding planet-forming disk would have been seeded with this same rich inventory of prebiotic material, delivered directly from the hot core of its own natal cloud. The water in our oceans and the organic molecules in our cells may have had their first stirrings in a place just like the Orion hot cores, forged in the sudden, violent shock waves of a long-vanished stellar explosion. These mysterious hot patches of gas are therefore more than just astronomical curiosities. They are potential cradles for the very chemistry that leads to life, revealing that the path from stardust to living cells might be shorter and more violent than we ever dreamed. But the nebula's reach extends far beyond the brilliant glow we see in visible light. Encircling the entire Orion complex on a scale so vast it defies easy comprehension lies one of its most elusive structures, the infrared loop. This is not an object you could ever hope to see with your own eyes, even through the most powerful optical telescope. It reveals itself only to instruments that can perceive the universe in the warmth of infrared light, appearing as a gigantic, faintly glowing arc that stretches across an incredible swath of the constellation. We're not talking about a structure a few light years across. This loop is immense, spanning hundreds of light years from end to end. To put that in perspective, if you could place it in our night sky, it would appear dozens of times larger than the full moon, a colossal, ghostly ring hanging in space. Its sheer size immediately sets it apart from the more localized dramas of the Trapezium Cluster or the Dark Bay, suggesting an origin story of correspondingly epic proportions. The central mystery of this loop is its very existence. What incredible force could possibly create such a perfectly curved, coherent structure on this monumental scale? The prevailing and most compelling theory points to a celestial cataclysm, a supernova. The logic is elegantly simple. When a massive star reaches the end of its life and explodes, it does not just vanish in a flash of light. It unleashes a titanic shock wave, an expanding sphere of energy and ejected material that races outward at millions of miles per hour. As this powerful blast wave plows through the interstellar medium, the thin soup of gas and dust that fills the space between stars, it acts like a cosmic snowplow. It sweeps up this material, compressing it, heating it, and forging it into a dense, luminous shell. We are essentially looking at the inner surface of a single, gigantic bubble blown in the fabric of space by a stellar explosion that occurred millions of years ago. The infrared loop is the lingering, fossilized remnant of that ancient supernova's expanding shock front, a permanent scar recording one of the most violent events in the universe. This theory, however, creates a fascinating and counterintuitive puzzle regarding the loop's relationship to the Orion Nebula itself. The two structures appear connected, part of the same cosmic tapestry, yet they are separated by a vast gulf of both space and time. The Orion Nebula is a relatively young feature, its stars only 1 million or so years old. The supernova that created the infrared loop would have had to explode long before the nebula's current stars were even born. This suggests a profound and layered history for this region of our galaxy. The exploding star was likely a member of a previous, much older generation of stars that formed in the same general area billions of years ago. Its death throes would have sent that powerful shock wave racing through space, carving out the cavity we now see as the loop. Millions of years later, that very same shock wave may have played a pivotal role in the birth of the Orion Nebula we know today. By compressing the gas and dust in its path, the ancient supernova shock wave could have triggered the gravitational collapse that began the formation of the molecular cloud now giving birth to the trapezium stars. In this way, the death of one generation of stars literally cleared the stage and provided the spark for the birth of the next, linking these two seemingly separate structures across eons in a continuous cycle of stellar death and rebirth. Further deepening the mystery are the peculiar motion and composition of the loop itself. Detailed measurements show that this enormous structure is not static. Different segments of it are moving at different speeds and in slightly different directions. This isn't the perfectly symmetric expansion we might expect from a single, simple explosion. The irregularities suggest a more complex history. Perhaps the shock wave encountered regions of varying density in the interstellar medium, causing it to slow down in some areas and speed up in others, warping its shape over time. Alternatively, the loop might not be the product of one single supernova, but the merged remnants of several smaller explosions from a cluster of massive stars that lived and died together. The loop's infrared glow itself provides another clue. Its light comes largely from dust grains that were heated by the initial shock wave and are now re-radiating that energy at infrared wavelengths. The specific properties of this emission reveal the composition and temperature of this swept-up material. offering astronomers a unique sample of the interstellar medium from a much larger volume of space than the nebula itself contains. Studying the infrared loop is therefore like reading a history book of the Orion region's most violent events, written in the heated dust and moving gas of a fossilized supernova remnant, a silent testament to the explosive forces that have shaped our galactic neighborhood for millions of years. Just next door to the grand spectacle of the Orion Nebula lies a quieter, yet equally mysterious neighbor, the Orion Molecular Cloud 2, or OMC2 for short. While it lacks the brilliant glow of its famous sibling, this dense, dark cloud is anything but a passive bystander. It is a deeply active participant in a complex cosmic dance, engaging in a series of gravitational and energetic exchanges with the main nebula that continue to baffle astronomers. The relationship between these two regions is one of the most intricate and least understood dynamics in the entire Orion complex, a hidden interaction that challenges our simple notions of how stellar nurseries evolve in isolation. The first layer of this strange relationship is gravitational. OMC2 is not simply floating nearby, it is gravitationally tethered to the main Orion Nebula cluster. Precise measurements of stellar motions show that the two clouds are pulling on each other, their mutual gravity influencing the paths of stars and the flow of gas between them. This tug-of-war is thought to be responsible for subtly distorting the shapes of both clouds, stretching them toward one another in a slow-motion embrace that has likely been ongoing for millions of years. This interaction may also be funneling material from the darker OMC2 into the brighter nebula, providing a fresh influx of raw fuel for star formation and potentially influencing the types of stars that are born there. It's a silent, invisible connection, but its effects are written in the very architecture of the region. Perhaps even more puzzling than the gravitational link is the clear evidence of an energetic exchange between the two clouds. Astronomers have detected faint but distinct filaments of glowing gas that appear to bridge the gap between OMC2 and the main nebula. This is deeply unusual because OMC2 is too cold and dense to be ionizing its own gas. It shouldn't be glowing at all. The leading theory is that these are not intrinsic emissions from OMC2 itself, but rather the result of irradiation from the main nebula. The immense ultraviolet radiation pouring out of the Trapezium Cluster is so powerful that it seems to be reaching across space and indirectly exciting the outer layers of its neighboring cloud. It's as if a brilliant spotlight were so intense that it accidentally illuminates the building next door, revealing details that would otherwise remain hidden in shadow. This energy transfer raises profound questions about how radiation can permeate a supposedly opaque molecular cloud and what effects it might have on the star formation processes happening deep within OMC2's shielded heart. The mysteries only deepen when we look at the star formation activity within OMC2 itself. Despite being a neighboring cloud of similar age and composition to the one that birthed the trapezium, its stellar population is strikingly different. It contains a notable absence of the massive, brilliant O-type stars that dominate the main nebula. Instead, its output is dominated by a larger number of smaller, lower-mass stars. This discrepancy is a significant puzzle. If both clouds started with the same basic ingredients, why did they cook up such different batches of stars? The answer may lie in the very interactions between them, the gravitational pull from the main nebula, or perhaps the pressure of its expanding ionized gas, might have disrupted the collapse of the largest, most massive cores in OMC2, preventing the birth of true stellar giants. Alternatively, the cloud could have been stripped of some of its densest material early on, siphoned away to feed the voracious appetite of the main nebula's star formation, leaving behind only lighter resources for its own stellar creations. This leads us to one of the most captivating oddities, the presence of what astronomers call seed stars or runaways. There is compelling evidence that several stars now residing in OMC2 did not actually form there. Their trajectories and velocities suggest they were born within the tumultuous core of the main Orion Nebula and were later ejected by violent gravitational interactions, only to be captured by the quieter gravitational well of OMC2. Imagine a chaotic party next door that gets so rowdy a few guests are thrown out into the yard, where they then settle down on your peaceful patio. These immigrant stars bring with them not only their own energy but also the chemical signature of their birthplace, creating a puzzling mix of populations within the cloud and offering a live demonstration of how star clusters can exchange members across light years. Finally, the cloud exhibits its own internal enigmas that seem disconnected from, yet may be influenced by, its vibrant neighbor. Deep within its cold depths, radio telescopes have detected sporadic and powerful maser emissions. Masers are the microwave equivalent of lasers, naturally occurring beams of intense, focused radiation typically generated by molecules like water or methanol in regions of energetic turmoil. The ones in OMC2 are exceptionally powerful and fluctuate unpredictably. Their behavior suggests periods of intense, localized activity around very young protostars' outbursts that could be triggered by sudden clumps of material crashing down onto the stellar surface. The question is whether the gravitational nudges from the main nebula, pulling and compressing gas within OMC2, are acting as a trigger for these violent accretion events, essentially turning the neighbor's gravity into a stir stick that agitates the cloud's internal dynamics. Orion Molecular Cloud 2, therefore, is far more than a separate entity. It is an integral part of a larger, interconnected ecosystem. Its strangeness is not born in isolation, but is a direct product of its relationship with the brilliant nebula next door, a constant reminder that in the cosmos, no island is truly ever alone. But the interplay of light and shadow within Orion is not confined to the grand structures of its core. It extends into a neighboring celestial formation that presents a mystery of a more subtle, yet equally captivating nature. Just to the north of the brilliant Orion Nebula lies a separate patch of glowing gas known as the Running Man Nebula. This region is a complex mix of emission and reflection, where hot gas emits its own light and cold dust reflects the light of nearby stars. It is here that we find one of the most intriguing optical plays in the entire constellation, a phenomenon that relies entirely on our perspective from Earth. Certain dark lanes of dust within the Running Man are aligned in such a way that they cast long, dramatic shadows across the glowing background. From our distant vantage point, these shadows coalesce into a shape that uncannily resembles a solitary, sprinting figure, a cosmic silhouette that has earned the nebula its popular name. This celestial apparition is, of course, a magnificent illusion. There is no giant humanoid form dashing through the cosmos. What we are witnessing is a chance alignment of incredibly dense, cold molecular clouds situated between the brilliant emission nebula and our line of sight. These clouds are so thick with sooty dust particles that they completely block the light from behind them, creating those stark, black silhouettes. The perceived motion of the Running Man is a static snapshot. The figure is frozen in a single moment, its apparent action a trick of pareidolia. The human brain's innate tendency to find familiar patterns, especially human shapes, in random data. It is the same psychological effect that lets us see animals in clouds or a face on the surface of the moon. The true scientific value of this illusion, however, lies not in the figure we imagine, but in the information encoded within the shadows themselves. These dark patches are far from simple voids. By carefully studying the precise edges and density gradients of these shadows, astronomers can perform a form of cosmic cartography. They can map the intricate structure of the dark dust clouds themselves, determining their thickness, density, and overall shape in 3 dimensions. It's akin to holding your hand in front of a bright lamp and studying the sharpness of the shadow it casts to understand the shape of your fingers. A very sharp, well-defined shadow indicates the obscuring cloud is dense and relatively compact, while a softer, more diffuse shadow suggests a more wispy, ethereal structure. In this way, the running man's shadow acts as a natural probe, revealing the architecture of otherwise invisible regions of the nebula. Furthermore, the interaction of light around these dark clouds tells another story. Look closely at the edges of the darkest shadows, and you will often notice a faint, reddish glow outlining them. This isn't just scattered light, it is the telltale signature of hydrogen gas that has been excited by the intense ultraviolet radiation from nearby stars. The dust clouds are not only blocking light, they are also being heated by it. This energy causes the gas mixed with the dust to fluoresce, painting the periphery of the shadow with a delicate, luminous halo. This reveals that these dark nebulae are not isolated entities, but are actively interacting with the energetic environment around them, being slowly warmed and eroded by the very starlight they currently block. The most fascinating aspect of this shadow play is its inherent impermanence. While the changes would be imperceptible over a human lifetime, this is a dynamic system. The fierce stellar winds from massive stars are constantly blowing, and the intense radiation is steadily evaporating the dusty material. Over thousands of years, the delicate structures casting these shadows will be slowly sculpted and reshaped, eventually worn away entirely. The silhouette of the running man will gradually blur, soften, and ultimately dissolve, its fleeting form a temporary monument to the ongoing struggle between light and darkness. It serves as a poignant reminder that the cosmos is not a static painting but a living, evolving entity, and even its most iconic illusions are merely brief scenes in a grand, continuous performance of change. Yet even these spectacular jets are not the largest or most energetic outflows found within Orion. Extending far beyond the compact Herbig-Haro objects on a scale that truly boggles the mind are the colossal structures known as the Orion fingers. Discovered relatively recently through advanced infrared and radio observations, these are not the delicate, glowing wisps of a protostellar jet. The fingers are something else entirely, a series of massive, bullet-like projectiles of gas, each one stretching an incredible 1.5 light-years in length and moving at speeds that defy belief, some clocking in at nearly 400 kilometers per second. Imagine a structure so vast it could easily span the distance from our Sun to its nearest stellar neighbor, and then picture dozens of these behemoths, all launched from the same general point in space and all racing outward in a coordinated, yet terrifyingly violent expansion. The most immediate puzzle they present is their bizarre and distinctive shape. As the name implies, they appear as long, slightly curved tendrils, often with a glowing, clumpy tip and a cooler, more diffused tail. They don't look like the smooth, continuous jets from a single young star. They resemble a series of massive cannonballs that have been fired simultaneously from a cosmic cannon, leaving behind turbulent wakes as they tear through the interstellar medium. This unique morphology is the first clue that their origin is not a simple, steady process. The leading theory suggests they were created by an event of almost unimaginable power, a catastrophic explosion that occurred deep within the core of the Orion Nebula within the last 1,000 years. This wasn't a slow eruption, but a sudden, violent release of energy that ejected massive clumps of dense gas all at once, like throwing a handful of pebbles into a pond. As these clumps rammed into the surrounding molecular cloud, they created the glowing bow shocks we see at their tips, while the stretched-out material behind them formed the long, trailing fingers. This explanation, however, only deepens the central mystery. What kind of event could possibly muster the energy required to launch such enormous masses of gas at such phenomenal speeds? The sheer kinetic energy involved is staggering, dwarfing the output of even the most powerful protostellar jets. Calculations show the total energy required is on par with that released by a supernova explosion. Yet, we see no evidence of a recent supernova remnant at the finger's point of origin. This has forced astronomers to consider even more exotic possibilities. The prime suspect is a dramatic gravitational encounter within a very dense, very young cluster of massive stars. If two or more stellar behemoths underwent a close fly-by or even a direct collision, the gravitational chaos could have literally ripped apart their surrounding disks and ejected these gigantic blobs of material in a single apocalyptic event. Another fascinating hypothesis involves the sudden and explosive ignition of a particularly massive protostar. As it rapidly accretes material and begins nuclear fusion, the resulting immense pressure and radiation could blow away its remaining cocoon in a violent, directional outburst, creating these massive outflows. But the mysteries do not end with their formation. The chemistry within the Orion fingers is just as peculiar as their physics. Spectroscopic analysis reveals an unusual and unexpected abundance of molecular hydrogen and iron within the glowing tips of these structures. Finding iron here is particularly confusing. Iron is a heavy element forged in the hearts of massive stars and typically dispersed throughout a nebula by supernova. Its presence in such high concentrations within these recently launched outflows suggests that the event that created the fingers did not just scoop up ambient cloud material. It must have dredged up material from very deep within the core, from a region enriched by previous generations of stars. It's as if the explosion not only blasted away the surface layers, but also excavated a deep trench, hurling material from the nebula's ancient past out into its future. This provides a fascinating form of cosmic archaeology, allowing us to sample the otherwise inaccessible deep interior of the Orion molecular cloud and revealing a history of stellar death and elemental recycling that predates the current brilliant nebula. The existence of the Orion fingers forces a profound reconsideration of the energy budget within stellar nurseries. We can no longer view star formation as a process driven solely by gentle collapse and steady accretion. The fingers are a blatant, spectacular testament to the fact that the birth of stars, especially the most massive ones, is punctuated by episodes of catastrophic violence. These events can release more energy in a single instant than a star will release over millions of years of its subsequent life. This has enormous implications for the environment of the entire nebula. The shock waves from the fingers' formation would have rippled through the cloud, compressing some regions to trigger new star formation while simultaneously tearing other regions apart and sterilizing them. They act as powerful mixers, churning the nebula's chemistry and redistributing materials across vast distances. The Orion fingers are not merely a curious side effect of star birth. They are a dominant, shaping force, a dramatic reminder that the universe often builds its most beautiful structures not with a gentle hand, but with the occasional, spectacular detonation. Yet, even as we marvel at these grand structures sculpted by starlight, a far more subtle and intricate drama is unfolding on a microscopic scale within one of the nebula's most defining features. We return now to the dark, geometric wall of the Orion Bar, but this time not to admire its imposing silhouette. Instead, we peer directly into its razor-sharp edge, into the chaotic frontier where the blistering ultraviolet radiation from the trapezium stars slams into the cold, dense molecular cloud. This boundary is known as a photodissociation region, and it is here that astronomers are uncovering a chemical mystery that defies every expectation, a place where the universe seems to be breaking its own rules to forge molecules in a way that simply shouldn't be possible. In an environment this harsh, the conventional wisdom of chemistry falls apart. The intense flood of ultraviolet photons should be a destructive force, a cosmic blender that tears molecules apart as soon as they try to form. Think of it as trying to build a delicate house of cards in the middle of a hurricane. The energy is so overwhelming that it prevents any complex structure from holding together. And for the simplest molecules, that's exactly what happens. But when scientists trained powerful infrared and radio telescopes on the Orion Bar, they detected the spectral fingerprints of something astonishing. a rich and diverse array of complex carbon-based molecules, including polycyclic aromatic hydrocarbons or PAHs. These are not simple compounds, they are large, multi-ringed organic molecules, the very same types of sooty particles found in automobile exhaust and chimney smoke. Finding them flourishing in a zone of such extreme radiation was like discovering a lush, thriving garden growing in the heart of a blast furnace. Their resilience is the first great puzzle of the bar. The mystery only deepens when we look at the specific types of energy these molecules are absorbing and emitting. The distribution of this energy is all wrong. In the laboratory, when you energize these molecules, they relax and emit their energy in predictable ways. But in the Orion bar, the energy patterns are bizarrely out of equilibrium. Certain molecular states appear overpopulated, glowing with an intensity that suggests they are being pumped full of energy by a mechanism far more efficient than simple starlight. It's as if the molecules are receiving energy not from a broad, general floodlight, but from a precise cosmic laser targeting specific energy transitions. This points to a highly specialized process at work, one where the terrifyingly destructive radiation field is actually being harnessed and channeled to drive very specific and very unlikely chemical reactions. So how is this possible? How does chemistry not only survive but actively thrive in what should be a sterile wasteland? The answer appears to lie in the unique, layered structure of the bar itself. The transition from ionized gas to neutral gas to molecular cloud is not a smooth gradient. It is an incredibly steep cliff face, changing over a distance smaller than our solar system. This creates a series of distinct chemical zones, each with its own temperature and density. Within this structured chaos, dust grains play a heroic role. These tiny particles of silicon and carbon act as microscopic shields and catalysts. A molecule can begin to form on the protected surface of a cold dust grain deep within the shadow of the bar. Then, a chance shock wave or a turbulent eddy might lift that molecule just high enough into the irradiated zone to be energized by the starlight, causing it to glow and revealing its presence to our telescopes before it is inevitably destroyed. It's a fleeting existence, a constant cycle of formation and destruction happening over breathtakingly short timescales. This process suggests a radical idea that the destructive ultraviolet radiation might not just be a breaker of molecules but also a maker of them. The immense energy could be providing the necessary activation energy for specific reactions that would otherwise be too slow to occur in the cold of the cloud. Furthermore, the sheer density of the gas in the bar means that even if a complex molecule has a very short lifetime before being torn apart, new ones are being formed so continuously that a steady-state population is always maintained. We are witnessing a form of cosmic chemistry driven by relentless, explosive turnover. The Orion bar is not a serene laboratory. It is a frantic, bustling factory operating at a breakneck pace, where the universe's most destructive forces have become, paradoxically, its most creative chemists. Diving into the heart of the Orion Nebula, we find its brilliant core powered by the Trapezium Cluster, a dazzling city of young stars. But this is no serene metropolis. It's a gravitational mosh pit where the stars are engaged in a frantic, chaotic dance that defies our most sophisticated computer models. When astronomers began meticulously tracking the individual motions of these stars over time, they expected to see a relatively ordered system, with stars smoothly orbiting the cluster's common center of gravity. Instead, they discovered a scene of pure stellar anarchy. Many stars are zipping around with wildly unexpected velocities, some hurtling along at speeds that seem to have no clear gravitational explanation. This isn't the gentle waltz of a mature star cluster. It's a violent, unpredictable scramble where close encounters are the norm and the rules of motion are constantly being broken. This frenetic activity points directly to a phenomenon known as dynamical relaxation. In a cluster as densely packed as this one, stars are constantly tugging on each other gravitationally. Over time, these interactions lead to a bizarre form of energy transfer. Through a series of gravitational slingshots, slower-moving stars can lose energy and sink closer to the cluster's core, while faster-moving stars gain energy and get ejected outward to the cluster's edges. The most extreme encounters can even fling stars completely out of the cluster altogether, sending them racing into the lonely depths of interstellar space as runaway stars. This process acts as a sort of gravitational sorting mechanism, but the sheer intensity of it in the Trapezium Cluster is far more violent than anyone anticipated, creating a dynamic and ever-changing stellar population. This leads us to one of the most perplexing mysteries, the case of the mysteriously missing massive stars. Our understanding of star formation suggests that a cloud as massive as the one that birched the Orion Nebula should have produced a certain number of truly colossal stars. Yet, when we take a census of the current population, those predicted stellar giants are simply not there. They haven't yet died in supernova. They should be shining brightly right now. So where did they go? The most compelling theory is that the same gravitational chaos that ejects smaller stars is even more effective at hurling out the most massive members of the cluster. Because of their immense gravity, close encounters between multiple massive stars can result in a gravitational slingshot of apocalyptic force, catapulting one of the stars out of the cluster at tremendous speed. We may have already found a few of these escapees, like the massive star Orion, which is blazing its way through space and whose trajectory, when rewound, points directly back to the Orion Nebula as its birthplace. The ultimate challenge posed by this stellar bedlam is its direct contradiction to our most advanced N-body simulations. When astrophysicists try to model the evolution of the Trapezium Cluster using every physical law we know, the virtual cluster they create on their supercomputers never quite matches the real thing we observe. The simulated clusters often appear denser, or their stars move in slightly more predictable ways. This discrepancy is a humbling reminder that we are still missing pieces of the puzzle. It suggests that the initial conditions of the cluster's birth were even more turbulent and chaotic than we've accounted for, perhaps involving subtle magnetic fields that aren't fully integrated into the models, or the lingering effects of gas that has since been blown away by stellar winds. The strange dynamics of the Orion Nebula cluster are more than just a curiosity. They are a crucial stress test for our fundamental theories of how stars form and interact, forcing us to refine our understanding of the complex physics that governs these beautiful, violent nurseries. And just when we thought we had seen the full spectrum of stellar tantrums, the nebula presents us with a jet so strange it seems to defy physics itself. This is Herbig-Haro Object 202, a cosmic squiggle that looks less like a laser beam and more like a frantic, tangled scribble drawn across the sky by an invisible hand. While most of the jets we've seen maintain a relatively straight path, HH202 is a spectacular exception. Its structure is a chaotic mess of kinks, curves, and abrupt changes in direction, telling a story of a protostar that cannot seem to make up its mind about where it's aiming its immense power. This isn't a steady flow. It's a series of violent, misaligned eruptions, each new burst of material punching through the nebula in a slightly different direction than the one before it, creating a bizarre and winding path of shocked glowing gas. The central mystery of this object is its profound instability. What could possibly cause a jet to change its direction so dramatically and so frequently? The prevailing theory points directly to the complex and dynamic magnetic fields generated by the infant star at its heart. We believe that the material for these jets is channeled along the protostar's powerful magnetic field lines, which act like a set of invisible railway tracks guiding the outflow. In a stable system, these magnetic tracks are fixed and the jet flows straight, but for HH202, the tracks themselves appear to be shifting. The star might be wobbling or precessing, causing its magnetic axis to tilt and swing around over time. Alternatively, the inner accretion disk feeding the star could be warping or experiencing violent instabilities, which would in turn distort the magnetic fields anchored within it. Each time the magnetic geometry changes, the jet's launch direction is altered, resulting in that bewildering corkscrew path through space. This presents an even deeper puzzle. What could cause such a profound shift in a star's magnetic architecture? The answer may lie in the possibility that this isn't a single star at all, but a very close binary system. If the jet is being launched from a protostar that has a companion orbiting very close to it, the gravitational tug from that companion could periodically disrupt the disk and destabilize the primary star's rotation, causing its magnetic field to wobble erratically. It's a stellar dance so chaotic that it whips the jet around like an out-of-control garden hose. The changing direction of HH 202, therefore, could be a real-time record of a violent gravitational relationship between two stellar infants, a celestial argument written in light across the nebula. Observing this object is like watching a key piece of a cosmic engine revealed. The twisting path of the jet provides astronomers with a unique window into the otherwise invisible magnetic processes happening right at the surface of a newborn star. By meticulously mapping each kink and curve, scientists can work backwards to model the strength and behavior of the magnetic fields that sculpted it. This bizarre, meandering jet is more than just a beautiful anomaly. It is a crucial diagnostic tool, helping us understand how stars regulate their spin, manage their growth, and ultimately how they shape the environments from which planets will one day form. Its chaotic nature underscores a fundamental truth about star birth. It is never a simple, linear process, but a turbulent and often messy affair, governed by the invisible and immensely powerful forces of magnetism and gravity. But as we pull our focus from these grand, violent structures and train our instruments on the seemingly insignificant, the individual specks of dust floating within the nebula, we uncover a mystery that is both microscopic and monumental. This isn't just ordinary space dust. The material that permeates the Orion Nebula, what we might simply call Orion dust, possesses a set of chemical and physical fingerprints so peculiar that it challenges our very understanding of where such materials come from and how they are made. When astronomers analyze the light that has traveled through this dusty haze, they don't see the simple, featureless absorption they might expect. Instead, the spectra are riddled with a series of bizarre, unidentified bumps and dips, a cryptic signature that points to a dust population unlike any we've studied in our own cosmic backyard. The first major anomaly is the sheer size and shape of some of these grains. In the cold, quiet depths of most interstellar clouds, dust is typically fine and powdery, made up of tiny silicate and carbon-based particles smaller than a fraction of a micron. But in Orion, evidence suggests the presence of much larger particles, some stretching to several microns across practically boulders by interstellar standards. Even more curiously, there are strong indications that many of these grains are not perfect little spheres. They appear to be elongated, fluffy, and highly porous, more like intricate fractal snowflakes than solid specks of rock. This bizarre morphology suggests a formation process that is far more active and complex than simple condensation. It's possible that the violent environment of the nebula, with its shock waves and turbulent gas motions, is acting like a colossal industrial mixer, constantly smashing small grains together in low-speed collisions. These collisions wouldn't shatter them. Instead, they would allow the grains to stick together in a process called coagulation, building up these large, complex, and fluffy aggregates over time. The chemical composition of this dust is where the story gets truly strange. The most prominent mystery involves a set of spectral features known as the Unidentified Infrared Bands, or UIBs. For decades, astronomers have seen these specific wavelengths of light being emitted from Orion and other nebulae, but they couldn't match the pattern to any known atom or molecule. After painstaking laboratory work, the prime suspects were identified as a class of large organic molecules called polycyclic aromatic hydrocarbons, or PAHs, essentially sooty particles made of linked rings of carbon and hydrogen. Finding these in Orion was expected. They are common in combustion on Earth. The anomaly is their incredible abundance and resilience. The ultraviolet radiation flooding the nebula should be shredding these delicate carbon rings apart, yet they are not only surviving, they are thriving, emitting their signature light with unexpected strength. This forces a rethink of their structure. Perhaps they are not free-floating molecules, but are instead sheltered within the protective matrix of those larger, fluffy dust grains, or they have unusually stable configurations that make them resistant to destruction. Perhaps the most profound implication of the Orion dust studies is the discovery of certain isotopic ratios that seem alien to our solar system. Isotopes are different forms of the same element that have varying numbers of neutrons in their atomic nuclei. By measuring the ratio of, say, certain isotopes of oxygen or nitrogen locked in the dust, scientists can get a read on the conditions under which that dust formed. Some of the ratios found in Orion don't match the standard blend we see throughout our own solar system. This is a staggering clue. It suggests that a significant fraction of this dust did not originate in the well-mixed cloud that gave birth to our Sun and planets. Instead, it might be genuine interstellar material, a sample of dust that formed around other stars in other parts of the galaxy that has somehow found its way into the Orion Nebula. We could be looking at the scattered remnants of ancient supernova or the shed atmospheres of long-dead red giant stars, a cosmic inheritance of pre-solar grains that hold the secrets of nucleosynthesis from across the Milky Way. This Orion dust, therefore, is far more than a simple ingredient for future planets. It is a diverse and ancient population of cosmic artifacts. Each strange, fluffy grain, with its unique chemistry and history, is a time capsule. Some particles may be pristine relics from the galaxy's earliest epochs, while others are newly forged in the nebula's violent current environment. Together, they form a complex chemical ecosystem that is busily processing simple elements into more complex ones. This dust is not passive. It provides surfaces for chemical reactions, shields molecules from destructive radiation, and will eventually become the raw material for new planetary systems around the nebula's stars. By studying its peculiarities, we are not only learning about Orion, we are peering into the very recipe book of the galaxy, uncovering the processes that create the fundamental building blocks from which worlds, and perhaps even life itself, are made. This puzzling age discrepancy strikes at the very heart of how we believe stars are born and mature. According to our most fundamental models of stellar evolution, stars that form from the same cloud of gas and dust should be essentially the same age. They are cosmic siblings, born from the same parent material in a single, brief burst of star formation that might last only a few million years. In a cluster like the Orion Nebula, that entire process should be over in a cosmic blink, leaving behind a group of stars that are all within a very narrow age range, perhaps only 1 million years apart. Yet when we apply our standard methods for dating these stars, the results tell a wildly different story, suggesting age differences of several million years between neighbors. It's as if you looked at a kindergarten class and found that while most children were 5 years old, a few of them appeared to be well into their teens. The primary tool astronomers use for this cosmic dating is the Hertzsprung-Russell diagram, a graph that plots a star's brightness against its color or temperature. Stars of a given mass follow a predictable path on this diagram as they age, allowing us to estimate their age by where they fall along that path. In a coherent cluster, all the stars should line up neatly along a single, well-defined isochrone, a line representing their common age. But in Orion, the stars are scattered. Some sit exactly where we'd expect for vibrant 1 million-year-old infants, burning bright and hot. Others, however, have already settled onto the main sequence, looking for all the world like more mature, settled stars that have been burning steadily for millions of years longer. This scatter is the core of the controversy, forcing us to ask whether our dating methods are flawed, or if something truly strange is happening in this nursery. One compelling explanation suggests that the age spread might not be an illusion at all, but a genuine reality. Perhaps star formation in this cloud wasn't a single, brief event but a drawn-out process that occurred in multiple waves over several million years. In this scenario, the nebula's core could have experienced successive bursts of collapse, with one generation of stars igniting and beginning to shine while the next was still just a coalescing knot of gas nearby. This would mean the Trapezium Cluster isn't a single family of siblings, but more of a cosmic neighborhood with a mix of older and younger residents. This protracted formation could have been driven by the very shock waves from those ancient supernovae we discussed earlier, which might have compressed different parts of the giant molecular cloud at different times, triggering separate episodes of star birth across eons. Another fascinating possibility is that the environment itself is playing tricks on us, making some stars appear older than they truly are. The Orion Nebula is an incredibly harsh place, bathed in intense ultraviolet radiation and scoured by powerful stellar winds. For the lower mass stars in the cluster, this brutal environment could be literally stripping away their youth. The fierce radiation from the massive trapezium stars might be eroding the outer, cooler layers of these smaller stars, effectively giving them a premature tan. By boiling away their outer atmospheres, the radiation makes these stars appear hotter, brighter, and bluer than they should for their actual age, tricking our models into classifying them as more evolved and therefore older stars. It's a case of cosmic mistaken identity, where environmental stress is masking a star's true nature. Furthermore, the gravitational pandemonium within the cluster could also be a factor. Stars that undergo violent close encounters or get ejected from their birth sites can have their internal structures disrupted, potentially altering their rate of contraction, and thus their apparent age on the Hertzsprung-Russell diagram. A star that has been gravitationally shaken up might contract and heat up at a different rate than one that has enjoyed a calm existence, leading to a misleading placement. This means the observed age spread might not reflect different birth dates, but rather different life experiences, a history of stellar trauma that has left some stars looking prematurely mature. Resolving this controversy is about far more than just accurately dating the stars in Orion. It forces a critical re-examination of the textbooks on stellar evolution. If the age spread is real, we must explain how a cloud can sustain star formation for so long against the disruptive feedback from the first massive stars that are born. If it is an illusion, we must drastically improve our models to account for how extreme environments and dynamical interactions affect a star's apparent age. The Orion Nebula, in all its brilliant complexity, is holding up a mirror to our understanding, revealing that the simple, clean stories we tell about star birth may need to make room for a far more complex and nuanced reality. But our journey through Orion's tapestry of mysteries doesn't end within the boundaries of its glowing gas. It extends outward across the void to a seemingly separate and distant structure known as Orion Molecular Cloud 3. To the untrained eye, OMC3 appears as just another dark, star-forming cloud in the constellation, a solitary neighbor. Yet, a deeper investigation reveals an astonishing and deeply puzzling connection. This isn't merely a cloud floating in the same general direction. Mounting evidence suggests that OMC3 and the main Orion Nebula are engaged in a complex, long-distance relationship, interacting across dozens of light years in ways that challenge our understanding of how celestial structures influence one another. The first compelling clue to this connection lies in the subtle architecture of the space between them. Radio astronomers mapping the faint whispers of molecular hydrogen have discovered faint, tenuous filaments of gas that appear to act as bridges linking the two clouds. These are not solid structures, but rather delicate tendrils of denser material cosmic pathways that suggest a past or even ongoing exchange of matter. The presence of these filaments implies that these two clouds are not truly independent. They are likely remnants of a single, much larger giant molecular cloud that fragmented millions of years ago. Some of the material between them failed to fully condense into one cloud or the other, leaving behind these ghostly threads as a lasting testament to their shared origin. It's a cosmic umbilical cord, a faint but undeniable link between a parent and its most brilliant child. Even more baffling than these material bridges is the evidence of synchronized activity. When astronomers compare the populations of young stars within OMC3 to those in the main Orion Nebula, they find a curious and unexpected alignment in their ages. Both regions show a distinct peak in star formation activity that occurred at roughly the same cosmic time. This synchronization across such a vast distance is incredibly difficult to explain. Star formation is typically triggered by local events: a nearby supernova shock wave, the compression from a passing spiral arm, or the gravitational collapse of a single, isolated cloud. For two separate clouds to light up with new stars in unison suggests they were both subjected to the same large-scale external trigger, a colossal pressure wave that swept through this entire region of the galaxy and squeezed both clouds simultaneously. This points toward a dramatic shared history, likely involving the same ancient supernova that created the infrared loop. The cataclysmic death of a massive star millions of years ago would have sent a powerful shock wave rolling outward in all directions. This wave would have taken eons to travel the distance between where the star exploded and the locations of the two clouds. If the wave reached both OMC3 and the main Orion cloud at approximately the same time, it could have initiated a wave of star formation in both places despite their physical separation. We are seeing the lingering echo of that single, apocalyptic event, a fossilized record of a shock wave that orchestrated the birth of stars across light years, tying the fates of these two clouds together across the millennia. The interactions may also be more direct and gravitational in nature. The immense collective mass of the Orion Nebula complex exerts a powerful gravitational pull on everything around it, including OMC3. This pull could be subtly distorting the shape of the more distant cloud, stretching it slightly toward its brilliant neighbor and potentially influencing the dynamics of star formation within it. Furthermore, there is tantalizing evidence of stellar runaways, stars that were ejected from the chaotic core of the Trapezium Cluster at high speeds. The trajectories of some of these outcast stars seem to point directly toward OMC3. It is conceivable that over thousands of years, these interstellar travelers have journeyed across the gulf between the clouds and are now entering the outskirts of OMC3, bringing with them fresh energy, metals, and perhaps even triggering new rounds of star formation upon their arrival. This would make OMC3 not just a cousin to the main nebula, but a recipient of its stellar exiles, a celestial sanctuary for orphans cast out from the turbulent heart of Orion. Yet woven invisibly through this entire tapestry of chaos and creation, holding it all together with an unimaginable force, is a phenomenon so fundamental it dictates the very rhythm of star birth itself, the nebula's magnetic field. For decades, the role of magnetism in Orion was thought to be a simple background player, a faint whisper in the cosmic storm. But recent observations have shattered that assumption, revealing a magnetic architecture of breathtaking complexity and surprising strength, a hidden skeleton that both supports and constrains the nebula in equal measure, presenting a puzzle that challenges our most fundamental ideas about how stars are born. The first clue to this magnetic enigma came from subtle studies of starlight. As light from distant stars passes through the elongated, needle-like dust grains within the nebula, these grains tend to align themselves with the local magnetic field like countless microscopic compasses. This alignment polarizes the starlight, giving it a slight preferred direction of vibration. By meticulously mapping this polarization across the entire nebula, astronomers can effectively trace the invisible lines of the magnetic field. What they found was astonishing. Instead of a chaotic, tangled mess of field lines which would be expected in such a turbulent environment, the maps revealed a large-scale, surprisingly ordered structure. Vast regions of the nebula show magnetic fields that are remarkably coherent, flowing in sweeping, organized patterns that seem to drape across the entire cloud complex, almost like a giant, invisible veil has been thrown over the constellation. This orderliness is the puzzle's first layer. In a region being blasted by powerful stellar winds and shock waves, the magnetic field should be a scrambled, fractured mess. The fact that it maintains such a high degree of organization suggests it is incredibly resilient, possessing a strength that was completely unexpected. The magnetic pressure in parts of the Orion Nebula appears to be powerful enough to rival the force of gravity and the pressure of the turbulent gas itself. This means the field is not just a passive passenger, it is an active, dominant force that can resist being twisted and torn apart by the nebula's violent motions. It acts as a powerful framework, providing structural support to the cloud against its own gravitational weight, potentially explaining why some incredibly dense regions like the Dark Bay have not yet collapsed to form stars. The magnetic field is simply too strong, holding the gas up like an invisible scaffold. The field's influence becomes even more apparent when we look at the birth of individual stars. The prevailing theory of star formation, called core collapse, relies on gravity pulling material inward. But in Orion, the magnetic field seems to be dictating the terms of this collapse. The field channels the flow of ionized gas, guiding it along its lines and preventing it from falling in radially from all directions. This can funnel material onto the growing star in a more focused, efficient stream, but it can also slow the overall process down by limiting the angles from which the star can feed. Furthermore, this magnetic guidance is likely the key to solving one of the biggest mysteries in star formation, the angular momentum problem. As a gas cloud collapses, it should spin faster and faster, just like a figure skater pulling in their arms. If this spin weren't somehow slowed, a star would fling itself apart before it could ever fully form. The magnetic field provides the perfect break. As the star and its disk rotate, they drag the magnetic field lines around with them. These twisting field lines then act like an elastic band, winding up until they transfer that rotational energy outward, flinging material away in the spectacular jets we see as Herbig-Haro objects. The strangely organized magnetic field isn't just a curiosity. It is the essential engine that allows stars to form at all, by solving the fundamental physics problem of how to shed deadly spin. However, the magnetic map of Orion is not one of perfect order. When we zoom in from the large-scale patterns to the sites of intense star formation, like the Trapezium Cluster, the picture becomes far more complex and contradictory. Here, the field lines show signs of extreme stress. They are bent, compressed, and twisted into knots. This is the battleground where the dynamic forces of stellar birth are fighting against the rigidity of the magnetic scaffold. In some areas, the field appears to be pinched, as if the gravitational collapse of a protostar is dragging the magnetic lines down into a deep well with it. In other places, the powerful outflows from massive stars have blown enormous bubbles, pushing the magnetic field outward and stretching it into a protective shell around the expanding cavity. These local distortions are critical. They show us the points where the magnetic field is losing its grip, where gravity and pressure have finally overcome magnetic support and triggered the collapse that leads to a new star. The field structure, therefore, gives us a direct real-time map of the balance of power within the nebula, revealing exactly where star formation is being allowed to proceed and where it is being forcefully postponed. The grandest mystery of the Orion magnetic field is its origin. How did such a strong and ordered field come to be? One compelling theory suggests it is a fossil relic, a remnant of the much larger, weaker magnetic field that permeates our entire galaxy. As the giant molecular cloud that became Orion slowly condensed under its own gravity, it would have pulled in these galactic magnetic field lines, squeezing them together and amplifying their strength in the process, much like a purse string gathers fabric. This could explain the large-scale order. Another, more dynamic theory proposes that the field is self-generated and constantly reinforced by the incredible turmoil within the nebula. The violent motions of ionized gas churned by stellar winds and shock waves could act like a gigantic dynamo, generating and sustaining a powerful magnetic field through a self-perpetuating cycle of motion and magnetism. The truth likely involves a combination of both, an inherited galactic field that has been dramatically amplified and reshaped by the nebula's own intense activity. Unraveling this origin story is crucial because it doesn't just apply to Orion. If such strong, ordered magnetic fields are a common feature of stellar nurseries, then they must be a fundamental ingredient in the recipe for star formation across the universe, a force we are only just beginning to appreciate and one that forever changes our understanding of the cosmic cradles where stars are born. And now we come to a structure that seems to defy the very nature of shadow and light we've just explored. This is the so-called Orion Bright Bar, a feature that appears to the eye as one of the most brilliantly illuminated ridges in the entire nebula. It arcs through the glowing gas like a celestial highway made of pure light, a stark contrast to the dark, silhouetted bars we discussed earlier. But here lies the brilliant deception. This isn't a solid, brightly lit object at all. The Orion Bright Bar is one of the nebula's most captivating illusions, a trick of geometry and perspective that reveals just how easily our eyes can be fooled by the vast depths of space. The secret to this illusion lies in our line of sight and the three-dimensional structure of the nebula. Imagine holding a brightly lit flashlight inside a vast, foggy room. If you point the beam directly at your eye, the light is blindingly intense. But if you look at the side of the beam from a 90-degree angle, you see its length cutting through the fog, and it appears as a defined, luminous column. The Orion Bright Bar is that column. We are not looking at a solid object that is itself glowing. Instead, we are looking directly down the length of a long, thin wall of gas that is being illuminated from behind and within by the fierce ultraviolet radiation of the trapezium stars. Our viewpoint from Earth gives us a perfect edge on perspective of this glowing wall, allowing us to see a tremendous depth of fluorescing gas all stacked up along our line of sight. This immense path length, filled with excited hydrogen, is what makes it appear so extraordinarily bright. It's not that the gas here is inherently more luminous, it's that we are looking through more of it than anywhere else, a cosmic chance alignment that turns a simple veil of gas into a blazing celestial landmark. The physics behind its intense glow is a dramatic story of stellar power. The bright bar is in essence the inner, illuminated face of one of the much larger and denser molecular clouds that sits farther from the Trapezium Cluster. The same destructive ultraviolet photons that are eroding the propellids and sculpting the pillars are slamming into this distant wall of gas, energizing it and causing it to fluoresce with that characteristic red light of hydrogen alpha emission. What makes this bar so sharp and well-defined is the incredible density of the gas at this boundary. The material is packed so tightly that it can resist the erosive force of the stellar wind for a time, creating that steep, cliff-like edge where the transition from ionized to neutral gas happens over an astonishingly short distance. This sharp gradient is what gives the bright bar its razor-sharp appearance, a clearly drawn line between the brilliance of ionized space and the dark, cold molecular cloud beyond. This particular alignment does more than just create a beautiful illusion. It provides astronomers with a unique natural laboratory. Because we are viewing the photodissociation region perfectly edge-on, we can study its structure with incredible precision. We can see how the different types of emission change across its face, from the highly ionized gas on the side facing the stars to the warmer molecular zones just behind it, and finally into the cold, dark depths of the cloud. It allows scientists to test their models of how radiation interacts with matter in a way that wouldn't be possible if we were looking at the structure face-on. The bright bar acts as a cosmic magnifying glass, letting us dissect the processes of photoevaporation and shock physics in exquisite detail, simply because of our fortunate perspective from a small planet over 1,000 light-years away. It is a permanent reminder that in astronomy, what you see is not always what you get, and that sometimes the most valuable scientific insights come from learning to decipher the universe's most beautiful deceptions. Yet, even within this hostile environment, a closer look reveals that not all proplyds are created equal, and their survival depends on a delicate interplay of several crucial factors. The most immediate and obvious factor is simple distance. A proplyd's location relative to the aggressive trapezium stars is its primary determinant of fate. Those that form in the nebula's outer suburbs, far from the intense core radiation, face a much gentler stellar wind. Their photoevaporation rates are consequently slow and manageable, allowing them to retain their mass for millions of years, and plenty of time for dust grains to coalesce into planetesimals and eventually full-fledged planets. Conversely, a proplyd born too close to the brilliant bullies of the Trapezium Cluster finds itself in a cosmic blast furnace. The unrelenting ultraviolet radiation bombards its surface, heating the gas to extreme temperatures and blasting it away at an astonishing rate. For these unfortunate disks, the prognosis is grim. They are living on borrowed time, often with expected lifespans of a mere 100,000 years before they are completely evaporated away, their potential planets never given a chance to form. However, distance is not the sole arbitrator of survival. The proplyd's own mass plays an equally critical role. Imagine two similarly sized ice cubes placed in the same warm room. The larger, denser one will naturally take much longer to melt completely. The same principle applies here. A more massive protoplanetary disk, one that is dense and packed with material, simply has more fuel to burn. Even under a fierce photoevaporative wind, it can lose a significant amount of mass and still retain a substantial reservoir of gas and dust for planet formation. It has the resources to weather the storm. A smaller, lighter disk, on the other hand, has no such safety margin. The same rate of mass loss will strip it down to nothing in a celestial heartbeat. This creates a stark dichotomy within the nursery. The rich get richer, with massive disks potentially forming planetary systems even in harsh environments, while the poor, the smaller, lighter disks face almost certain dissipation before their planetary dreams can ever be realized. The geometry and orientation of the disk add another layer of complexity to this survival struggle. A proplyd that presents its full broadside to the onslaught of radiation, like a shield facing an enemy, will experience the most intense heating and the highest rate of evaporation across its entire surface area. But a disk that is tilted on its axis, or one that is partially shielded by a fortunate alignment with a dense knot of gas or another proplyd, might only have its outer edges scoured by the stellar wind. This can create a protected pocket in its inner regions, a sanctuary where temperatures are cooler and conditions are more stable for the delicate process of planet formation to begin. This sheltered environment might even accelerate the growth of rocky worlds, as the external radiation boils away the lighter outer gases, effectively concentrating the heavier dust and rocks in the inner disk and providing a richer concentration of building blocks. Perhaps the most fascinating protective mechanism is one that seems counterintuitive: the photoevaporative wind itself. As the intense radiation blows material off the disk's surface, this outflowing wind can actually form a protective barrier. It creates a dense, ionized layer of gas that acts as a buffer, absorbing and deflecting some of the incoming ultraviolet photons before they can penetrate deeper into the disk's vulnerable core. In a way, the disk is sacrificing its outer layers to save its heart, using its own evaporating material as a shield. This self-regulating process highlights the incredible dynamism at play. It's not a simple story of destruction, but a complex feedback loop where the very process of erosion can sometimes trigger mechanisms that slow that erosion down. Ultimately, the proplyds of the Orion Nebula present us with a powerful cosmic metaphor. Their fight for survival, dictated by their location, their inherent strength, and a little bit of random luck, mirrors the unpredictable and often harsh nature of existence itself. Their varied fates demonstrate that the path from a swirling disk of dust to a stable planetary system is fraught with peril, and that the environment of one's birth can be just as important as the materials one is born with. By studying which disks survive and which succumb, we gain invaluable insight into the conditions that might make a planetary system habitable, or even whether it gets to form at all. These tiny, glowing cocoons are not just beautiful, they are the key to understanding our own origins, revealing the fierce and magnificent struggle that precedes the creation of every world. But if we truly want to understand the lifeblood of this stellar nursery, we must look beyond the solid-seeming structures and brilliant stars to the medium that connects them all, the gas itself. The Orion Nebula is not a static painting. It is a dynamic, churning ocean of plasma, and mapping its currents reveals a hidden layer of motion that is every bit as strange and beautiful as the more obvious wonders. When astronomers began using sophisticated instruments to measure the Doppler shifts in the light from different parts of the nebula, they expected to see a relatively simple expansion, a gas flowing outward from the central cluster under the pressure of stellar winds. Instead, they discovered a chaotic and breathtakingly complex ballet of circulating flows, countercurrents, and high-speed jets that paint a picture of a system in a state of turbulent, energetic upheaval. The most immediate and large-scale surprise was the discovery of what can only be described as a circulating weather pattern within the nebula. While there is a general outward flow of material, it is far from uniform. Vast cells of gas, each light years across, appear to be circulating in giant convection-like loops. Hot, ionized gas, heated by the trapezium stars, rises from the central regions, expands, and then cools slightly as it reaches the nebula's outer edges. There, it appears to sink back down, only to be reheated and recirculated back into the heart of the storm. This isn't a simple one-way street out of the nebula. It's a massive, ongoing recycling program where material is constantly being churned and mixed. This circulation has profound implications for the nebula's chemistry, as it transports freshly processed elements from the hot interior out to the colder, molecular outskirts, and perhaps brings new, pristine material from the outer clouds back into the intense radiation field for processing. Woven through this large-scale weather system are mysterious, high-velocity flows that seem to have no connection to the obvious sources of power. By carefully analyzing the subtle shifts in spectral lines, astronomers have identified narrow filaments and streams of gas moving at velocities that can exceed 100 kilometers per second. These aren't the focused jets from protostars which have a clear point of origin. These are more like rogue currents, rivers of fast-moving material cutting through the slower-moving background gas. Their paths are often curved and don't always point directly away from the central cluster. The energy required to accelerate these massive streams to such speeds is immense, and their origins remain one of the nebula's most compelling cold cases. The best guess is that they are the lingering shock fronts from ancient energetic events that occurred within the cloud long before the trapezium stars switched on. Perhaps the echoes of that same BNKL explosion, or the death throes of a previous generation of massive stars whose supernova remnants have since faded from view. These flows are like ghostly signatures of past cataclysms, their energy still imprinted on the gas, shaping its motion millions of years after the initial detonation. Perhaps the most telling motions are found at the interfaces between different regions, particularly at the sharp boundary of the Orion Bar. Here, the measurements reveal a scene of incredible violence. The ionized gas on the side facing the stars is racing away at tremendous speed, ramming into the cold, dense molecular cloud behind it. This collision creates a shock front of astronomical proportions, a continuous, supersonic crash where the advancing wall of hot plasma slams into the stubborn resistance of the cold cloud. The velocities involved are so high that they heat the gas at the contact point, creating the bright, narrow ridge we see and triggering a cascade of complex chemical reactions. This is the nebula's ongoing construction zone, where the irresistible force of starlight meets the immovable object of a molecular cloud, and the resulting turmoil is what continuously forges new structures and seeds the environment with the raw materials for future stars and planets. The motion of the gas is the real story of the Orion Nebula, a story of ancient explosions, powerful stellar engines, and a continuous, chaotic dance between creation and destruction that shapes every single feature we see. But beyond the violent tantrums of individual stars and the chaotic circulation of gas lies an entire population of stars that, for centuries, remained completely hidden from our view. This is the Orion Infrared Cluster, a secret society of stars shrouded behind such a thick veil of dust that they are utterly invisible to optical telescopes. Their discovery was a revolution that came not through a larger lens, but through a shift in perspective by observing the universe in the warmth of infrared light. What we found there was not just a few hidden points of light, but a teeming metropolis of stellar formation operating in near-total darkness, a parallel universe of star birth with its own bizarre set of rules and characteristics. The defining feature of these stars is their profound obscurity. They are embedded deep within the densest, coldest cores of the Orion molecular cloud, enshrouded in cocoons of gas and dust so thick that they can absorb virtually all of the visible light their surfaces emit. It's like trying to see a light bulb through a blanket of black felt. The photons simply cannot penetrate the countless tiny dust grains in their path. This is why this cluster remained a secret for so long. But while visible light is blocked, the heat generated by these forming stars, the thermal energy from their gravitational collapse and the warmth of their surrounding dusty blankets leaks outwards as infrared radiation. This longer wavelength light can travel through the dust where visible light cannot, finally revealing the hidden stellar nursery to our specially designed telescopes. What makes these stars so unusual is the environment of their birth. Unlike the stars in the Trapezium Cluster, which formed in a region that was subsequently cleared and illuminated by its most massive members, the stars of the infrared cluster are still in the process of emerging. They are forming in extreme isolation, buried in conditions that more closely resemble the primordial state of the nebula millions of years ago. This has profound effects on their development. Shielded from the harsh ultraviolet radiation that is evaporating the proplyds in the main nebula, these stars are able to hold onto their natal material for much longer. This allows them to grow to larger masses and, crucially, to retain massive, rich disks of gas and dust that are pristine laboratories for planet formation, untouched by the destructive forces that plague their cousins in the brighter parts of Orion. The existence of this robust cluster forces a major question. Why would star formation proceed so vigorously in such a dark, seemingly quiet part of the cloud? The answer appears to be that it's not quiet at all. The trigger likely came from the same ancient shock waves that shaped the rest of the region. The powerful pressure wave from a long-ago supernova would have rippled through the entire molecular cloud, compressing even its deepest, darkest cores to the point of collapse. This external trigger, rather than internal processes, may have been the spark that ignited this hidden generation of stars. Furthermore, the very darkness that defines them provides a key advantage. Without the intense radiation pressure from nearby massive stars to disrupt the process, gravity can work more efficiently, pulling material together in a more calm and collected manner. This might allow for the formation of a different distribution of stars, perhaps with a higher proportion of mid-sized stars and fewer of the extremely massive, short-lived varieties. Studying the Orion infrared cluster is like discovering a perfectly preserved fossil that reveals an earlier stage of stellar evolution. It shows us that the brilliant Orion Nebula we see is just the visible tip of the iceberg, the cleared out and illuminated showroom. Meanwhile, the real factory, the bustling industrial heart where stars are still being forged on a massive scale, continues to operate in the shadows, hidden from view but revealed in glorious detail by the infrared eye. This secret cluster reminds us that the most significant cosmic action often happens behind the scenes, and that to truly understand a stellar nursery, we must learn to see the light we cannot see. Yet for all its grandeur and violence, the nebula holds a more subtle secret, one written not in the motion of its stars or the shape of its dust, but in the very chemical elements that compose it. When astronomers began to take a detailed inventory of the Orion Nebula's composition, they expected a relatively straightforward result. After all, the cloud from which it formed was a typical giant molecular cloud, and the processes of nucleosynthesis inside stars are thought to be well understood. The recipe for a nebula, it was assumed, would be fairly uniform, but the data told a different story, revealing a baffling patchwork of chemical abundances that vary wildly from one region to another, creating a puzzle that challenges our understanding of how elements are forged and distributed throughout the cosmos. One of the most immediate surprises was the bizarre and lopsided distribution of helium. This primordial element created in the Big Bang should be smoothly mixed throughout the nebula. Instead, observations show clear and significant concentrations in some areas and curious deficits in others. This shouldn't happen under normal conditions. Helium is an inert gas, and its atoms don't readily form molecules or freeze onto dust grains that would allow them to clump together. Its uneven spread suggests that the nebula's history is far more turbulent than its current appearance might suggest. The leading theory points to the intense, searing radiation from the trapezium stars. This powerful ultraviolet light is so energetic that it can actually separate helium atoms from their electrons, ionizing them. Once ionized, these helium ions can interact with the nebula's magnetic fields in complex ways, potentially being channeled and concentrated in specific zones by the invisible magnetic architecture that permeates the region. The helium map, therefore, might be less about chemistry and more about physics, a ghostly tracing of the powerful radiation fields and magnetic currents that flow through Orion's heart. The helium puzzle is just the beginning. The real chemical enigma deepens when we look at the heavier elements, particularly oxygen and nitrogen. In the fierce light of the Trapezium Cluster, atoms are stripped of their electrons, and we can see the spectral signatures of these ions clearly. What we find is deeply confusing. In some parts of the nebula, the amount of oxygen appears to be significantly lower than the cosmic average, almost as if something has been secretly siphoning it away. The prime suspect for this theft is none other than the nebula's own dust. Astronomers believe that a substantial fraction of the oxygen atoms have effectively gone into hiding, locked away inside icy mantles that coat countless tiny dust grains. In the cold, sheltered depths of the molecular cloud, oxygen readily freezes onto these grains, forming water ice and other oxygen-rich compounds. When a shock wave from a nearby stellar explosion or a powerful jet heats the grains, these ices can be released back into the gas, but the process is uneven, creating those puzzling regional deficits and surpluses. Nitrogen, on the other hand, tells a completely different story. In the hottest, most intensely irradiated zones right next to the massive stars, nitrogen appears to be overabundant. This isn't because there's more of it, but because it behaves differently. Nitrogen is harder to ionize than oxygen, so while the fierce radiation blasts oxygen atoms to a highly ionized state that is difficult to observe, nitrogen atoms stubbornly hold onto their electrons, making them appear more prominent in our spectroscopic measurements. It's a classic case of a celestial illusion where the relative strength of a spectral line doesn't always reflect true abundance, but rather the specific physical conditions that make one element easier to see than another. This means that to understand the true chemical makeup of the nebula, we must first become master detectives of its plasma physics, decoding how temperature, density, and radiation strength conspire to hide and reveal different elements. The most profound chemical mysteries, however, involve complex molecules, the building blocks of something far greater. Deep within the cold, shielded cores of the Orion molecular cloud, radio telescopes have discovered a veritable factory of organic chemistry. We're not talking about simple compounds. We're finding molecules like methanol, formaldehyde, dimethyl ether, and even tentative signs of the simplest amino acid, glycine. Finding this sophisticated chemical soup in the cold vacuum of space was astonishing enough, but the real shock is their distribution. These molecules are not evenly spread. They are concentrated in very specific, isolated hot cores, often associated with deeply embedded protostars. This patchiness reveals that the formation of these life's precursors isn't a slow, steady process, but a dramatic one, likely triggered by sudden bursts of energy. The prevailing theory is that the violent shock waves from newborn stars, the same ones that create the Herbig-Haro objects and the Orion fingers, provide the necessary kick. A passing shock wave can compress a pocket of gas and dramatically heat it for a few thousand years, providing the energy needed for simple atoms to link up into complex chains. Then, as the region quickly cools again, these newly minted complex molecules freeze onto the surfaces of dust grains, preserving them like insects in amber. This process of shock-driven, flash-heated chemistry suggests that the ingredients for life are not forged in calm, quiet laboratories, but in the violent, chaotic birth cries of stars themselves. The strange chemical abundance patterns of the Orion Nebula are therefore more than just a curiosity. They are a historical record. They tell a story of cataclysmic explosions, intense radiation fields, and violent shocks that have churned and cooked the cloud's material over millions of years. Each anomalous concentration, each puzzling deficit, is a clue to a past event, a fingerprint left by a supernova, a stellar collision, or a powerful jet. By reading this chemical map, we are not just analyzing a nebula's composition. We are piecing together the violent and creative history of the cosmic nursery that may have given rise to our own solar system and ultimately to us. But as grand and eternal as this stellar nursery appears, its current brilliance is only a fleeting chapter in a much longer cosmic story. The Orion Nebula, for all its fiery spectacle, is not a permanent fixture in our night sky. Its eventual fate is a subject of intense debate and fascinating speculation, a mystery that forces us to consider the impermanent nature of even the universe's most magnificent structures. Within a surprisingly short time on a cosmic scale, the entire landscape we see today will be utterly transformed, and the forces that are currently building this celestial empire will be the very same ones that ultimately lead to its dissolution. The most immediate and certain future for the nebula is one of gradual evaporation and dispersal. The mighty engine driving this change is the Trapezium Cluster itself. These massive stars are living fast and will die young, but even before their dramatic finales, their relentless output of ultraviolet radiation and stellar winds is continuously blowing the nebula apart. They are like brilliant but destructive landlords, methodically dismantling the very house they live in. This process of photoevaporation is already clearing out a vast cavity around the cluster. Over the next 100,000 to a million years, this expanding bubble will grow larger and larger, pushing the remaining gas and dust outward and thinning it to the point where it will no longer glow with the characteristic red light of hydrogen. The iconic visual spectacle of the Orion Nebula will simply fade away, leaving behind a more scattered and diffuse cluster of stars visible against the dark backdrop of space. The nursery will have effectively closed its doors, its raw materials either used up in star formation or blown back into the interstellar medium to one day form part of a new cosmic generation. This straightforward story of dispersal, however, is complicated by the wild card of the nebula's most massive residents. The fate of stars like Theia to 1 Orionis C is to end their lives in spectacular supernova explosions. When these events occur, they will inject a catastrophic amount of energy into the already disrupted nebula. A supernova blast wave will rip through the remaining gas at thousands of kilometers per second, compressing some regions into new, sudden waves of star formation while violently shredding and scattering others. This could create a second, much more violent phase of the nebula's evolution, a final fiery punctuation mark that completely remodels the neighborhood. The timing and sequence of these explosions are critical unknowns. If the most massive stars explode in quick succession, their combined energy could completely sterilize the region, preventing any further star formation and leaving behind only a dispersed stellar association. If the explosions are more staggered, the shock waves from one could trigger the collapse of gas clouds that were previously stable, leading to a final burst of stellar birth just as the nebula's main era is concluding. The greatest uncertainty lies in the dark, dense reservoirs like the Dark Bay and the Orion Molecular Cloud. These regions are currently shielded from the destructive radiation, holding onto immense amounts of mass. Will the advancing wave of ionization from the Trapezium Cluster eventually reach them and begin to erode them away, or will their own gravity win out, causing them to collapse and form a massive new wave of stars long after the current bright nebula has faded? This is a central tension in predicting Orion's future. Some models suggest these cold clouds are the true future of the Orion complex, destined to ignite into a new stellar nursery that could one day outshine the current one. Others argue that the feedback from the existing massive stars will eventually penetrate and disrupt even these bastions of gas, preventing large-scale collapse and ensuring the entire region slowly winds down. The answer depends on the delicate and poorly understood balance between the supportive pressure of magnetic fields and internal turbulence within these clouds versus the crushing external pressure from the surrounding hot gas and radiation. What remains after this drama plays out will be a gleaming but more commonplace open star cluster. The trapezium stars will be gone, having ended their short lives in supernova, leaving behind their quieter, longer-lived lower mass siblings. This cluster will gradually drift apart over hundreds of millions of years, its stars spreading out along their own orbits around the galaxy. Each of these stars will carry with it the chemical legacy of its birth planetary systems, potentially enriched by the complex organic molecules forged in the nebula's violent heart. Our own solar system likely emerged from a similar environment billions of years ago, meaning the future of the Orion Nebula might already be written in the past of our Sun. The ultimate mystery, the one that technology may never fully resolve, is what kind of worlds and perhaps even life might arise from the specific ingredients being cooked in Orion's cauldron today. As our telescopes grow more powerful, they will not be able to watch this story unfold in real time. The timescales are far too long, but they will find other nebulae at different stages of this life cycle, allowing us to piece together the full story of Orion's future by observing the present states of its countless cosmic cousins. And so, our journey through the heart of the Orion Nebula comes to a close, but the true takeaway is not a set of answers, but a profound appreciation for the depth of the questions that remain. We have wandered through a cosmic gallery of impossible structures and bewildering forces, from the geometric perfection of the Orion Bars and the fleeting, shadow-cast Running Man to the high-speed chaos of the Orion Fingers and the serene, hidden empire of the infrared cluster. We've witnessed the tragic beauty of the proplyds locked in their race against time and felt the invisible might of magnetic fields that shape the very architecture of star birth. We've pondered stellar tantrums, ancient explosions, and chemical factories operating in the most hostile of environments. Each phenomenon a unique puzzle piece in a picture far larger than we can currently see. What becomes overwhelmingly clear is that the Orion Nebula is so much more than a pretty picture. It is a dynamic, chaotic, and infinitely complex ecosystem. Every mystery we've explored, the anomalous age spread of its stars, the bizarre chemistry of its hot cores, the unpredictable variability of its central engine, to one Orionis C doesn't just confuse astronomers, it fundamentally deepens our understanding of how universes build their stars and planets. These aren't mere curiosities, they are the clues that force us to rewrite our textbooks, to build better telescopes, and to think more creatively about the physics that governs all of creation. The nebula teaches us humility, showing us that for every rule we think we've established, nature has an exception waiting in the wings, more magnificent and baffling than the last. Now we turn the conversation over to you. Which of these 30 wonders captured your imagination the most? Was it the haunting, biological elegance of the pillars, the secretive journey of the Becklin-Neugebauer Object, or the sheer destructive creativity of the Herbig-Haro jets? Perhaps the silent, waiting potential of the dark bay resonated with you, or the grand, fossilized story of the infrared loop. Share your thoughts in the comments below. We are endlessly fascinated by what captures your sense of wonder. As we look to the future, with next-generation instruments like the James Webb Space Telescope peering ever deeper into these cosmic nurseries, one thing is certain: the Orion Nebula is not done surprising us. Every answered question will inevitably unveil 10 new mysteries. Will we find clearer evidence of those ancient supernovae? Will we witness the direct collapse of a cloud core into a black hole? Could we even detect the faint, tentative signatures of prebiotic molecules on distant forming worlds? The greatest revelation may be that the universe's capacity for wonder is infinite, and places like Orion are our front row seat to the show. Keep looking up and keep wondering. The next great discovery is waiting.